though this is very hard. So as soon as you get something that is a little bit like hard to game, you should like go for it and try it. And then preferably have some gradient. As well mentioned, if it's just binary and just a string check, that will be complex by nature of many of the problems which don't have like a first order logic answer, yes or no, right?
Yeah.
And
lastly, the model like partial credit, right?
Exactly. Yeah. And you want the model to know that it was going in the right direction. Like here in this case, we could have thought of adding some rewards for reading in the right file. Like it knows it read in the right file, maybe just the reasoning is wrong.
Right. So teaching person.
Yeah, that's a little bit how I think about it. Right, and then limit the tool calls output length because it's just going to make your training very slow and also going to confuse the model. So if you can work on outputting only what is necessary, that will make it more efficient across the board. I think that's also very reasonable for any agents and not just training.
Totally. And it saves you money too. You don't want to shove tons of useless tokens into the context window. So yeah.
Totally. All right.
Awesome.
Cool.
Thanks so much for that. That was incredible.
No, thank you.
Analysis and all the plots, charts.
Thank you, Will and Theo, for walking us through that. I'm really excited about this next segment, our customer spotlight. We're going to hear directly from the research engineer Sampriti at Cognition. So please welcome Sampriti.
Hey everyone, I'll quickly take over screen sharing. Is that good?
Yeah. As long as it's coming from your computer.
Yes, thank you, Theo, Will, and Christine. So hi everyone, I'm Sampriti. I work as a research engineer at Cognition. At Cognition, we build Devin and Windsurf. So Devin is an autonomous AI engineer that works independently on solving tasks in your code base. And as part of my work at Cognition, I work on improving like models to make parts of Devin smarter. So I'm really excited to share like what we've been working with Will and Theo on the agent RFP feature. So one of the tasks in Devin, like when you give initial query to Devin, one of the first thing it does is it goes into planning mode to kind of try to figure out what it needs to do to like actually solve this task. And from a UX perspective, we don't want the agent to spend too much time in planning mode because we want Devin to start working and like showing edits to the user as soon as possible. And so one of the motivations of this was, can we like fine tune GPT-5 or other frontier models like that better so that they get to this editing stage as quickly as possible while still maintaining or even improving accuracy. So the way we designed this task is, given the initial user prompt, we wanted to restrict the set of tools that's available to Devin. So in this case, it's just read file and shell because we don't really need to make any edits at this stage. And then we let the model explore or the agent explore and like figure out how to like which files to look at and which files to edit to solve this task. So in this case, we just have the read file and shell tool. The motivation of the shell tool is so that the model can run commands like grep and find to like search the code base for like certain strings that the user might have put in the query, or just look for like certain file names or things like that. And so as you mentioned earlier, so we need obviously the tool calls and then the dataset and the reward. So for the dataset, we collected a bunch of real world repositories and collected user queries from those repositories, and then we labeled what are the files like the user actually edited to solve this task. And ideally, we want this sub-agent to return those exact files so that in the following on, the agent can continue and make edits to those files. And then for the reward, we use the metric called F1 score. So F1 score balances both precision and recall. This is because we want the model to obviously like not just like if we just say precision or just a recall, the model would either like be very conservative and only return a few files, or like return too many things to try to get everything. And obviously, we want to be in the balance so that the agent that comes along after does not have to like the context is not polluted with too much data.
If we look in depth, this is a very cherry-picked example, but you can see the baseline model doing the search 6 times in a row before doing list-cast, another search and cat, whereas the fine-tuned model just follows a very simple policy of search and then cat and cat. And you can see that the number of repeats drops significantly from 1,000 to 500. So we just divide by 2. So the model is much better at understanding, making the right tool call the first time, so it doesn't have to repeat the exact same following with slightly different parameters. And if we look in depth, this is a very cherry-picked example, but you can see the baseline model doing the search 6 times in a row before doing list-cast, another search and cat, whereas the fine-tuned model just follows a very simple policy of search, list, and cat, and then it probably just reason on the output to correct a final answer.
Yeah, totally. Yeah, I just want to add that on this benchmark, the documents in the train set and the documents in the validation set, there's no overlap in the documents that are required to answer the question. However, the model is kind of still operating on the same pile of documents. So it still has access to basically the entire file structure, but the questions that are asked, there's basically no overlap in the documents that are required. So in some ways, it kind of like learns how to use this file system and like knows what documents are inside. But ultimately, the documents are kept separate.
Yeah.
So
yeah, that's pretty cool.
So that would probably match potentially your business use case where you have this existing corpus that you want to learn how to use better.
Yeah, totally. Yeah. All right, yeah, cool. So that was a quick demo. You will find the code if you want to go through it and run it. And very high level, we also have some advice on how to get successful with Agent RFT. So the first one is you need a well-specified and constrained task. And this is mainly in the sense where you need consensus from people who have domain knowledge or aesthetic for some visual tasks, where there is one real answer in a way, or people agree on what the good answer is. And this is very important because you want to share some signal to the model that is consistent and not say in one example, oh, answer A is good, and the next one answer A is not good, because then the model will get confused and will not learn how to reason better. Yeah. The second one is non-zero baseline performance. So we saw initially in our variance plot, you need the model to be sometimes right, or else if it's just never right after running like 100 times on the same sample, it will probably never learn. And especially if it's like this across your whole data set. Right. And then improve accuracy at K. So that's very interesting. If you run multiple times for each sample, and then instead of looking at the average performance, you look at the average performance for the best trajectory of each of the samples. That gives you some information on again the variance and how often does the model get it right. And so during training, we're going to nudge all the trajectories to go and match those best trajectories. Yeah. And technically, you can then bootstrap on this because you'll generalize across other samples, and so you'll bring in some new reasoning patterns and probably keep on pushing, and you can do that multiple times. And finally, is quality over quantity. In this example, we use 1,000 training samples, which is something which is quite a large number. I've done a lot of engagements with many less samples, probably 100, 150, and we've been quite successful. And again, the idea is really on how good the data is, and you don't want any mixed signals to the model.
Right. Yeah.
All right, so that was like on the performance side and what you do beforehand. Now on the infrastructure side, really related to our product, what you want to do is you want to mirror production behavior. You have the opportunity to host your tools, so just go for it, make it like very similar to production, and like that, everything that you're improving during training will actually translate to your product. Then the second part is investing in designing your grader. So the grader will really affect the way the model behaves, and so the model policy. And so it's very important to have it be aligned with your domain knowledge to make it hard to game and to hack. Though this is very hard, so as soon as you get something that is a little bit like hard to game, you should like go for it and try it. And then preferably have some gradient. As well mentioned, if it's just binary and just a string check, that will be complex by nature of many of the problems which don't have like a first order logic answer, yes or no. Right?
Yeah.
And
Kind of like
lastly,
the model, like partial credit, right?
exactly,
Yeah.
and you want the model to know that it was going in the right direction.
Yeah,
Like here in this case, we could have thought of adding some reward for reading in the right file. Like it knows it read in the right file, maybe just the reasoning is wrong.
Right. So teaching person.
Yeah, that's a little bit how I think about it. Right, and then limit the tool calls output length because this is going to make your training very slow and also going to confuse the model. So if you can work on outputting only what is necessary, that will make it more efficient across the board. I think that's also very reasonable for any agents, not just
Totally. And it saves money too. You don't want to shove tons of useless tokens into the context window. So yeah.
Totally.
Awesome.
Cool.
Thanks so much for that. That was incredible.
No, thank you.
That analysis and all the plots, charts.
Thank you,
Yeah.
Will and Theo, for walking us through that. Really excited about this next segment, our customer spotlight. We're going to hear directly from the research engineer Sam Pretty at Cognition. So please welcome Sam Pretty.
Hey everyone, I'll quickly take over screen sharing.
Hey.
Is that good?
Yeah. As long as it's coming from your computer.
Yeah.
Awesome. Yes, thank you, Theo, Will, and Christine. So hi everyone, I'm Sampriti. I work as a research engineer at Cognition. At Cognition, we build Devin and Windsurf. So Devin is an autonomous AI engineer that works independently on solving tasks in your code base. And as part of my work at Cognition, I work on improving like models to make parts of Devin smarter. So I'm really excited to share like what we've been working with Will and Theo on the agent RFP feature. So one of the tasks in Devin, like when you give initial query to Devin, one of the first thing it does, it goes into a planning mode to kind of try to figure out what it needs to do to like actually solve this task. And from a UX perspective, we don't want the agent to spend too much time in planning mode because we want Devin to start working and like showing edits to the user as soon as possible. And so one of the motivations of this was, can we like fine tune GPT-5 or other frontier models like that better so that they get to this editing stage as quickly as possible while still maintaining or even improving accuracy. So the way we designed this task is, given the initial user prompt, we want to restrict the set of tools that's available to Devin. So in this case, it's just read file and shell because we don't really need to make any edits at this stage. And then we let the model explore or the agent explore and like figure out how to like which files to look at and which files to edit to solve this task. So in this case, we just have the read file and shell tool. The motivation of the shell tool is so that the model can run commands like grep and find to like search the code base for like certain strings that the user might have put in the query, or just look for like certain file names or things like that. And so as you mentioned earlier, so we need obviously the tool calls and then the dataset and the reward. So for the dataset, we collected a bunch of real world repositories and collected user queries from those repositories, and then we labeled what are the files that the user actually edited to solve this task. And ideally, we want this sub agent to return those exact files so that in the following on, the agent can continue and make edits to those files. And then for the reward, we use the metric called F1 score. So F1 score balances both precision and recall. This is because we want the model to obviously like not just like if we just say precision or just a recall, the model would either like be very conservative and only return a few files, or like return too many things to try to get everything. And obviously we want to be in the balance so that the agent that comes along after does not have to like the context is not polluted with too much data. So yeah, we can get to the eval results. So we started off with GPT-5 based model being somewhat lower than like the current frontier model. And we ran two experiments. So one experiment was GPT-5 with like a smaller data set of around 100 samples. So 100 tasks across varying repositories. And then a larger experiment with around 1,000 samples. So one thing we tried to maintain was that the set of repositories would be distinct or disjoint between the train and the eval case, because we want to make sure it wasn't that like the model was just learning things about the data set. Because ideally, like when we want to use this in real life, the train model will never see certain repositories because it will be private repositories. So as you can see, like even with a smaller data set, it already obviously beats the base model by quite a lot. And even with the larger data set, we get an even further boost. And the plan action score here is basically the F1 score. So we take a look at all the files the model looked at, and also at the end, the model does output like what it thinks the right files to edit should be, and we can compare that with the labeled ground truth. So during the experiment, some of the things we noticed are that the model starts learning how to do a lot of parallel tool calls. So if you look at the traces, the first action that the model does, it will like kick off like 8 different things. Because like listing the repos, grabbing for things, and then following on, it will like once it gets the results from those tool calls, it will like independently explore all of those things, but again running more parallel tool calls. And usually because running the tool calls such as read file is quite a bit faster than like the actual like the model inference, it does help a lot that like these back and forths are like reduced quite a lot. So I think in the eval score, for example, when we put this in Devin, directly we noticed that to get to the originally on the baseline, to get to the end of the planning mode, it would take around 8 to 10 back and forths with the agent or with the model. But with the fine-tuned model, we would be done in like 4 back and forths. So that like cuts time in half by almost 4. Obviously, there's a thing where like sometimes the model could run a tool call that takes a longer amount of time. So we do try to penalize things like if it tries to do too many tool calls because it does take a lot of time or things like that. And also during training, we did have to kind of penalize if the model took too long because we don't want the model to like keep exploring and like never be satisfied. So yeah, we noticed that like with this agent RFP feature, we can just push like already frontier model like GPT-5 even further on like a specialized task when we have a clear reward of what we want to optimize. For the infrastructure, as you mentioned earlier, we run both the tool calls as a remote endpoint as well as the grader. And so the way the training works is every step the platform like sends us a bunch of rollout requests. So basically, like the model tries, given a certain sample, it tries to like does the rollout in like there's like around 32 copies or something like that for each. And so for each rollout, we spin up a new VM and like run the tool calls in this VM, and then the results are given back to the platform or the RFP grader. And then at the end, when we get the final answer, we call it grader endpoint where we compare the trajectory. So we look at the list of all the tool calls that the model made in that particular rollout, as well as the final answer, and we give a score based on the labeled ground truth. So in this case, we decided to go with like isolated VMs because we didn't because as you know, remember we used like a shell tool, so the model could decide to do some destructive actions. So we didn't want to like one rollout to affect the other rollouts in case the model goes crazy and runs RMR or something like that. And obviously, like we use VMs because we could reuse the production Devin VM info where we give every Devin instance a VM, but I think containers work well for this purpose as well. And some of the interesting things we noticed was that the RL is quite bursty. So at the beginning of every rollout, they would send us like 500 new rollout requests. So they definitely need to like handle that because that's like 500 new VMs starting at the same time. And then the other kind of like foot gun is that sometimes like let's say there's an infrastructure error and the VMs fail. It does like what ends up happening is the model gets 0 reward because like the tool calls fail and like the model can't figure out what's going on. And while that's not the model's fault, it does lead to the training kind of collapsing or like the model learning in a bad way because even the model might have done something good but got a 0 reward. So it is good to have a lot of monitoring on like when there's tool call failures or like there's abnormal issues with the model. Because sometimes it could be that the model just has formatting issues and it's not calling the tool correctly. But other times it could be just our info issue. But anyways, thank you to Will and Kathy for helping me debug all of these issues.
And Dylan,
shout out to
all the other people, yeah, for sure.
Yeah, and anyways, it's been really exciting to try this agent RT feature and being able to tune the performance of GPT-5 even more.
Yeah, thank you.
Back to you.
Yeah, it's incredible. Thanks so much for working with us so closely on this, and really glad to ship an agent to you. That's like beating the save the art team. So yeah. Do we have questions for this part?
Yeah. Let's go through some success stories too that we can share, and then we do have quite a bit of questions, so I want to make sure we have enough time for that.
All right, sounds good.
Thanks, and Pretty. We will catch you later.
Thanks so much.
Thank you.
Bye-bye.
All right, so yeah, we've seen a good success story with
Thank you so much for working with us so closely on this, and really glad to ship an agent to you. That's like beating the save the art team. So yeah. Do we have questions for this part?
Yeah. Let's go through some success stories too that we can share, and then we do have quite a bit of questions, so I want to make sure we have enough time for that.
All right, sounds good.
Thanks, and Pretty. We will catch you later.
Thanks so much.
Thank you.
Bye-bye.
with one of whom I worked really closely with Ambience, and
Work
Ambience,
closely with all of them.
yeah, no, that's true. But Ambience is a healthcare company, and they're embedded in some hospitals. And one of the tests that they look at is ICD-10 coding, and they have an agent for this. And ICD-10 coding is actually the work that you have to do when you want to do billing after a session with a patient, and you have to map the topics or the illnesses, the diagnosis actually of what you've discussed with some codes. And those codes are very precise, and there are like 70K of these codes. So it's quite a hard task. And what we're looking at here is we have a transcript between the doctor and the patient, and automatically from that transcript we want to propose the right ICD-10 codes. And this requires a lot of nuanced understanding of the discussion, but also a lot of medical reasoning. And that's why Ambience looked at GPT-5 and was using GPT-5. And one of the aspects is that it has to be quite fast, and so they use GPT-5 with low reasoning because of the way that the doctors use it. And so if you look at the plot on the right hand side, we started with GPT-5 low, hovering around the 0.5 F1 score, and then we built that agent that actually has a tool that does a search for those ICD-10 codes, and then we actually RFC'd that model. And you can see the jump from 0.52 to 0.57. It might look slightly small, but the actual highest performance you can get is around 0.70, 0.75, because we are looking at a task that is slightly subjective, and doctors agree or not on what are the actual codes. So this is a really significant jump for them. And not only we're seeing this increase in F1, the fact that we are fine-tuning, as we've seen during the whole session, also allowed them to reduce the latency. And so there's a 18% average response time, and that actually halves the number of samples that are above their latency threshold in the product. So that was a great use case, and it was great working with Brandon, Patrick, and the team. And then regarding another use case, very different, no more healthcare. Here we're looking at GenSpark, slides creation agent. So GenSpark has amazing agents, and one of them is an agent that builds slides. So the user will communicate with the agent to make different tool calls, and at the very end, those slides sometimes are not aesthetically necessarily very pleasing. There's a bit too much text, or they're too long, and therefore they use a reasoning model to try to harmonize all the outputs. And this is what we fine-tuned on. And what was great working with Flame and team was that they worked a lot on their model grader and different type of graders to judge both the content and the visual aspect of it, and they were extremely happy with the output. And I also find those slides quite pretty on the right-hand side that we have. And in terms of numbers, it provided like 88% improvement on bad cases over the existing models, which is a significant number that they were very happy with. So yeah, we'll have other use cases.
Yeah, absolutely. And we should use GenSpark for the next build hour slide. These look great. Yeah, so moving on, just to show you how diverse the success stories on Agent RT can be, we have we're close with Mako to build a GPU kernel building agent. So Mako is building agents to write these GPU kernels, which is really difficult for LLMs because there's just a scarcity of training data out there compared to other domains. Especially true for new hardware. So if NVIDIA puts out a new accelerator, there just aren't enough examples of performant kernels. But using Agent RT, as few as 100 PyTorch prompts were enough alone for GP5 to learn how to write fast kernels for a new hardware platform, as long as you have a good grader, which is what Mako worked really hard on. And that allowed us to not need any code examples actually to start writing these really performant kernels. So the fine-tuned model actually beats the state of the art by 72% in writing correct and performant GPU kernels, which is a huge boost. And lastly, we worked closely with Rogo. Rogo is building a financial reasoning agent. It's capable of reading financial filings, extracting investment insights, and then supporting human analysts through this question-answer interface. And they wanted to fine-tune O4 Mini to summarize and present these key findings from earlier steps in the finance workflow. So Rogo is really interesting. They use a custom LLM as a judge grader that was accessible via endpoints, so that we called their custom grader that measures the agent's factual accuracy, reasoning completeness, financial soundness, clarity of explanation. So you can see how you can just fit a lot of your own criteria and your own rubrics into your own custom grader, which is the power of the part of the power of the Agent RT platform. The results are fantastic with a 21% increase in core ML performance, with much lower hallucination rates and missing citations. I also just want to call out that Rogo did a ton of work in kind of making their grader unhackable. I think earlier runs showed that the model actually started reward hacking. So what happens with these with the RT process sometimes is that if you have an edge case in your grader, the model is super smart and sneaky, and it'll find ways to kind of exploit that grader. So it's also really important to make sure that your grader is pretty watertight, and that's what Rogo did. They made the grader watertight. They detected the hack, and as a result, the true performance that you're trying to optimize the model on just started shooting.
Yeah, I remember there was one Rogo run where we came back on the platform that we showed earlier, and the average reward and validation was this one.
Yeah,
100%.
That's too good to be true.
Yeah. All right, so that was for the customer.
So let's wrap up. So just to summarize, So let's talk about when to turn to agent RFT. So the general process that we recommend is first you want to make sure that you build this really high quality data set where your training and eval sets closely match your production traffic. So you kind of want the agents to not be surprised when you kind of go from like fine tuning it to actually exposing it to showtime. And second of all, you're probably on this journey of improving your agent performance. So you want to figure out what the baseline performance looks like, so you know where to improve from there. So you probably want to run these baseline evals against GPT-5 or whatever models you like using, and then from there you want to try to optimize the performance without fine tuning, because that's often one of the easier ways to get better performance out. You might want to adjust other parts of the task, like improving your prompts, improving your infra, improving your task harness, and then after you've squeezed out all the juice out of the task and base model, that's when you turn to agent RFT to further optimize and start changing the weights of the model to be fundamentally better on your task and your domain in an end-to-end fashion. Awesome.
Yeah, thank you, Will.
Okay, great. Let's move on to Q&A. We have a ton of questions, so wanted to make sure we had enough time for them. So maybe just let's go to the next slide and we can tackle them.
Cool.
Yeah.
Content task is best suited for agent RFT. You want to take this one? Oh, okay. All right. So I would take on this. So obviously, we've explored and explained a lot of ways in which you should kind of structure your data set or make sure that your data points have no variance in them, so that during exploration, the model actually knows what the difference between a good and a bad data point looks like. So fundamentally, you do want a training set where, hey, you still haven't squeezed all the juice out of it, but the model, given enough exploration, can figure out what a kind of good performance looks like. So that way, you can kind of hill climb. So that's one thing that I would say. Another thing I would say is, there's a task itself, but then there's the way that you're evaluating and grading it. And if the way that you're grading it is in a binary fashion, then it's going to be really hard for the agents to hill climb or kind of gradually get better and better and improve on that task. So you want to make sure that, yes, you have the task itself, but you also have how you're evaluating it. So those two things generally lead to quite a bit of success. You want to talk about maybe domains or other things you have?
Yeah, in terms of domains, it was quite surprising. I think we showed it with the customer stories, but it's really widely applicable. So I see agent RFT, as you presented very, very clearly at the beginning, something for any type of agents. And as soon as you have an agent that uses tools that are out of distribution of what we train our machine model on, which will naturally happen because you have your own tools, then this is really an opportunity for you to dive in on agent RFT. And if there's a lot of reasoning associated with it, that's even better to use GPT-5 or a very strong reasoning model.
Totally.
Yeah. All right, what's different about the RFT platform now and since it debuted in May? Well, I'll take this one even if Will's the one who built it, but and team, obviously, and the whole team.
A big team.
But what I really like about agent RFT now is, well, there's multiple things. In May, we're only able to fine-tune O4 Mini with a very specific set of graders. Now you're able to fine-tune O4 Mini or GPT-5 with tools and with endpoint graders. So the flexibility is just incomparable, and you can tackle pretty much, so many new tasks. And what is great here is that with this, you can actually create features in your product that just did not exist before. The model was not good enough. Now you have the path to actually, other than prompting, help the model to use those tools well and to build a product that you actually want. So for me, that's the most important. And then I want to work also on the observability of the platform and those different curves and all the stability. All of this has improved a lot, and that's right.
Totally, yeah. Yeah, and I also just want to kind of emphasize that with agent RFT, we're now in this multi-step RL paradigm. So with the original RFT platform, you give them all the prompts, the model thinks for a while, and then spits back an answer to you. But now you can actually do this multi-step thing. So the model is now in this loop with your world and with your environment, and all of that actually gets trained on end-to-end with your reader. So
yeah, that's awesome. Christine, do you have any other questions from
yeah, why don't we go to, if you go to the next slide, I was refreshing during. Okay, so if you're able to refresh, otherwise I can just read them out loud. Let's see.
Sorry, slideshow. So here's why RFT is sample.
Go back. I think we.
No, that's way up first.
Oh, okay.
Take it.
This one, right?
Yep.
Okay, cool. Do we have one after this, or?
Yeah.
Okay, there's more. Okay.
We can run a bit
All right,
over.
sounds good. Okay. Yeah, why is RFT sample? Okay, so this is sort of a question around like why maybe RL is sample efficient. I mean, we could talk at length about that, but fundamentally, first of all, the model is basically generating its own training data through the exploration process. So remember how we talked about this compute multiplier thing, like how the model is exploring the search space? Well, it's actually generating its own training data through that sampling process. And when you give it the grade or the reward at the end, that tells the model how well it's doing based on the trajectory rollout that it generated. And that actually ends up being the thing that we train the model on. So we obviously do a bunch of like reinforcement learning stuff over that trajectory, and we take your reward or your grade and we kind of apply it over the rollout in certain ways. But ultimately, the model is generating its own data.
Yeah. I'll also add a note on the fact that we're working on a frontier model and fine-tuning the frontier model. So the prior that you're working on is very strong already, and probably already has success on your task. So all of this variance only works because that model just is able to sometimes get it right.
Exactly.
And so it's just the power of the prior. And so if you think also and you continue to separate, if there's a new model that is stronger and you have RFT on it as well, you can expect also it to be sample efficient again because the prior will keep on increasing.
Yeah, the model is generating really good data for itself basically because the prior is so good as Dave said. So yeah. All right, let's see what the next one is. How does the RL training objective function differ from Gen RFT and agents take RFT? All right, sure. I'll start. So so there's a difference between the actual RL loss function and the actual reward. So the reward is what we allow you to specify. So whether this be reward functions that are native in our platform, for example, the string check grader that we kind of dissed on earlier with a model grader, or your endpoint grader. And so with that reward, we do stuff with that reward. So that would be the RL or reinforcement learning like loss. So that might be what you're asking about actually. So that so far doesn't differ between Gen RFT and agentic RFT. So we don't change the loss part. We may try new things as we're doing our research and research engineering to deliver even like bigger model gains. But for now, honestly, there's no difference. The main difference is now you can define much more flexible reward functions.
Yeah, and I think that's super important. When you look at base RFT, because you don't have access to the chain of thought, you only have access to really the final output. Whereas when you look at agentic RFT, you do have a lot of information on the traces, and Sampriti even mentioned it, grading those tool calls.
Yeah.
And so you can have much more control on the policy that you want to see for your model after training. So that's one big difference.
Totally. We have a little bit left. Should we try to?
Yeah, let's run over them. We can run over if people are free to stay.
Okay, that's good. Cool. Is RFT when there's a new response of the model, does the new model learn automatically from previous? Is this like if there is a new response of the model? So it's talking about like domain shift. For example, like you train the model on like a set of data points, but then you evaluate on.
Yeah, I'm not exactly sure. The way I see it, maybe ties in with all this idea of different trajectories that we run. And technically, any new response generated by the model is a new trajectory, and we actually do leverage this when we compute the objective. So my answer would be yes.
Yes, during training.
If that's understanding.
During training, yeah, but when you're doing inference, then like we're not using whatever you have during inference to go back and make the model better continuously. Not yet, at least someday.
All right.
Yeah.
Cool. Great question.
Yeah.
You can read it, yeah.
I guess so. Okay. Are the alpha endpoints used in the code available to everybody? I guess it depends on which alpha endpoint we're talking about. So
Is the alpha implicit as a tool in the grader?
Yeah.
Yeah.
Okay. Oh, yeah. Okay. So no, they aren't, and that's where the agent RT interest form comes in. So this is a functionality that is that we're exposing, and is something that is more or less in, like, I don't want to say private beta, but it's the type of functionality that we want to work with you to make sure that you get the most success possible on. So this is something that we'd love for you to talk to your friendly neighborhood account executive or account director at OpenAI to see how we can work together on.
Yeah, and that question is such a good segue, right?
Yeah, exactly.
Yep.
So we can wrap up with some resources on the right here. Feel free to explore these, but if you're interested in learning more about Agent RT and specifically working with our team here, check out this link, this tiny URL, fill out the interest form, and we will be in touch. And with that, I will share one more slide on upcoming build hours. So join us on December 3rd for Agent Memory Patterns. This will be the last build hour of our agent series, but many more build hours to come. Check out our homepage there below, and we'll keep adding them. So thanks, everyone, and we'll see you next time.
Thank you.
Yeah, thank you. Bye.
Welcome to OpenAI Build Hours. I'm Christine on the startup marketing team, and today we brought back Prashant and have Theo joining us for the first time.
Hi.
So today's topic is on reinforcement fine-tuning, or RFT. But before we begin, we will start with the goal of Build Hours, which is to empower you with the best practices, tools, and AI expertise to scale your company using OpenAI APIs and models. So at the bottom of the screen, you have our homepage, and this is where you can find all of our resources, as well as watching any past Build Hours on demand. So I'm going to give you a snapshot of what you can expect in the next hour. So first, we're going to be giving you an intro to RFT. We'll go through all the benefits of RFT, optimization, and then actually setting up a task. And then my favorite part is the demo will actually be live building, and I'll drop the link to the code repo in the chat so you guys can check it out and follow along. And then finally, we have a really exciting customer spotlight today. We have the co-founder and CEO of Cordance in the room with us, and he's going to be coming on and sharing the real world application of RFT. And then finally, we will end with Q&A. David will answer some questions, and then Theo and Prashant will be here to answer questions as well. Our team's also in the room, so feel free during the hour, if anything comes up, to drop your questions in the Q&A chat. You have to toggle a bit between the chat and the Q&A, but this is where you can submit your questions, and we'll answer them during the hour. So Prashant, Theo, feel free to take it away.
Great, thank you, Christine. All right, so let's start by orienting ourselves around where fine-tuning and reinforcement fine-tuning more specifically fits into model customization. So if you're trying to improve the performance of your LLM app, there's really two broad levers that you have. The first is to improve what the model knows. This can be handled with context engineering techniques such as better prompting or retrieval augmented generation, and also to improve how the model reasons. That's the second lever. This is where fine-tuning comes in. So if you're missing knowledge, start with prompting and RAG, but if the model knows the facts but still struggles to apply them or reason about them accurately, that's where fine-tuning would come in. We remind everyone that fine-tuning is an investment. So you must make sure you squeeze everything you can from the other levers that I just mentioned, and only then should you reach for fine-tuning. Today, we offer 3 techniques for fine-tuning on our platform. The first one, which is supervised fine-tuning, allows you to feed prompt and answer pairs, so the model can learn a fixed pattern. This is great for simple classification tasks or making the model adhere to a output pattern. Structured outputs also does this, but supervised fine-tuning can be useful for things like custom code formats. The next technique is called reference fine-tuning. Here, you give the model example of better and worse outputs, and the model sort of learns to mimic the tone or style of the better outputs and just prefer the one that you don't prefer. This is great for marketing copy, chatbots, and places where personality is important. And today, we're going to focus on reinforcement fine-tuning. Here, instead of labeled answers, you actually give our system a grader. And a grader is basically a rubric or a rule that allows the model to score responses for accuracy. The reinforcement fine-tuning system explores the solution space, grades different solutions that it comes up with, and improves itself. This technique has been found to be super powerful for policy compliance, legal reasoning, and medical workflows. Really any domain where reasoning matters. So let's quickly touch on the benefits of reinforcement fine-tuning before digging into the details. RFT is unique because it's the only method today that can be applied for reasoning models, and reasoning models, we believe, are the future. It's also data efficient, so you only need tens to hundreds of examples to get started with reinforcement fine-tuning, and it's much easier to get signal on whether your task will improve by applying this technique. And finally, it doesn't require these manually labeled outputs. As I mentioned, it operates using graders, and so you can focus more time figuring out a grading strategy, which is really useful for other things like evaluation, rather than sinking a lot of resources into building large legal data sets, which are quite expensive to curate. Today, teams are using RFT to replace complex policy pipelines with a single reasoning agent. They're also using it to improve compliance checks by training on real policy logic, and to boost accuracy in medical coding tasks with expert verified graders. Next, we'll have Theo show us how it works under the hood.
Yeah, thank you, Prashant. So now let's have a quick look at what happens under the hood and some aspects that actually make RFT so sample efficient in a way. So when you look at RFT, you start with your task, which is your data set, probably your prompt and your answer. And then you choose a model. Here we'll be focusing on O4 Mini that's available on the platform right now. And then there's the grader that we mentioned. So here, under the hood, the way the algorithm is going to run is like it's going to sample multiple times the same example and then a different reasoning path and then a new answer. And so the model will be able to compare all those different answers and therefore tell what is good and what is bad. And therefore one example actually provides a lot of information and a lot of insights on what is a good reasoning path to follow, what is a less good reasoning path to follow. And by training on tens or hundreds of samples, you actually improve the reasoning and so the generalization on that specific task. And that's why we love RFT.
Nice. So this is really different, right, from the other techniques we talked about, because one sample in those techniques is just one training example. And here we're pulling so much more signal out of a single task.
Exactly. You get many trajectories out of it, and that helps us be efficient.
Great.
Your task, which is your data set, probably your prompt and your answer. And then you choose a model. Here we'll be focusing on O4 Mini that's available on the platform right now. And then there's the grader that we mentioned. So here, under the hood, the way the algorithm is going to run is like it's going to sample multiple times the same example and then a different reasoning path and then a new answer. And so the model will be able to compare all those different answers and therefore tell what is good and what is bad. And therefore one example actually provides a lot of information and a lot of insights on what is a good reasoning path to follow, what is a less good reasoning path to follow. And by training on tens or hundreds of samples, you actually improve the reasoning and so the generalization on that specific task. And that's why we love RFT.
Nice. So this is really different, right, from the other techniques we talked about, because one sample in those techniques is just one training example. And here we're pulling so much more signal out of a single task.
Exactly. You get many trajectories out of it, and that helps us be efficient.
Great.
All right, now let's look at the task setup. So we're going to present first our dataset, and the dataset that we're using here and for the task is going to be a classification task where, given a legal text, we have to predict which EuroVoc level 1 classes it belongs to. So EuroVoc level 1 classes are the highest level, broadest thematic categories in the EuroVoc thesaurus, and this is a multilingual controlled vocabulary maintained by the Publications Office of the EU. And there are 21 different classes, and each sample can have 1, 2, up to 6, or even more classes assigned to it.
Cool. Let's look at one of those samples.
Yeah, awesome. Let's do that. So here you'll see on the left-hand side, there's a sample, a very short sample. It's the shortest we could find in the dataset. And then on the right-hand side, the reference answer where you can see there are 2 classes, which are employment and European Union. And if you want to follow along, you can find the dataset on Hugging Face. We plug the link here, but it's also in the code when we run the dataset exploration. So first, now that we have the dataset, how are we going to evaluate it?
Yeah, we talked a lot about graders already. So we're going to preview a little bit of how the grader is going to work by talking about the metrics that are important for a classification task. So this is probably not new if you have been doing machine learning for a while, but just to catch everyone up, the 2 metrics we really care about in a classification task are called precision and recall. And instead of giving the academic definitions, some of which are up here on the screen, I'd really love for us to build some intuition for what each of these mean. So precision can be thought of as a measure of figuring out of the predicted labels, how many of the labels are actually correct. So that's precision. And then the other metric we care about is called recall. And this really measures how many of the actual labels did we find. So did we return all the labels that we expected for a specific sample, or did we miss them? And then finally, on the last line here, we have an F1 score. And an F1 score is a composite sort of mean score between these 2 values, which weights the lower value slightly higher, right? So we expect to be bottlenecked on a classification task by sort of whatever's less in terms of precision or recall, and therefore we've chosen this measure. The reason it's important to have the F1 measure here, even though it's like less intuitive than the other 2, is because sort of mean score between these 2 values, which weights the lower value slightly higher, right? So we expect to be bottlenecked on a classification task by sort of whatever's less in terms of precision or recall, and therefore we've chosen this measure. The reason it's important to have the F1 measure here, even though it's like less intuitive than the other 2, is because the reinforcement fine-tuning system really requires a single grade for each training sample, right? So while we will measure precision and recall separately, as you'll see in a bit, we really need to provide a single composite score, and F1 allows us to do that. That being said, I think there are valid situations where you might choose a different way to like combine these 2 precision and recall metrics, right?
Yeah, totally. If you value recall more than precision, you might use an F2 score, which balances the 2 terms a bit differently, and you can train with that.
I'm going to have to ask you what that is later.
Okay. All right, so let's dive into the demo. So we've seen very high level what our data set looks like, and we have the grader and we know what model we're going to look at. So because we're in the machine learning task, we need to do some data exploration. And in particular, with reinforcement fine-tuning, really the quality of your data is primordial, and it's going to allow you to hold time on your data set or not, and to generalize on all the samples you can see or not. So I have set up a quick code. We're just showing the data set. You can probably do that on your end as well. And we'll build the items that are expected for Eval's platform and for RFT. So this is a very simple example where you have an item, we give it an ID, a text input, and a reference answer. And sorry about that. Just before, when I go to the first sample, I wanted to show you. Here you can see what it looks like under the hood in Hugging Face. So you have the text, and then you have some categories as well, which I clearly messed up. But here are the categories, and you have IDs in the categories. And those IDs represent the EuroVoc concepts, and they are just identifiers. And that's not ideal for the model because they have no semantic meaning. So what we want to do next, which I skipped over, is actually transform those IDs into names. And the reason why you want names is that the model is going to be able to reason over them in a much better way than over IDs. Does that make sense?
It does, yeah. Although I have to say, I might enjoy the challenge of having to guess 10014 for one of these.
I'll let you do that in the future. Right now, we'll focus on trade finance and all the other classes that exist. And so I'm splitting the dataset into, I'm selecting 150 samples randomly from the dataset. And the reason why I choose 150 sample, 100 for train and 50 for the validation, is to show that RFT can really be sample efficient. And with only 100 samples, we can actually get decent improvement. And then the 50 samples in validation are mainly to have a robust indication of how it performs on some data.
This data set we're using is quite large, right? How many samples does it have?
Yeah, in total, I think it has 7,000 samples, but it's across 23 languages, so it starts to scale up.
Nice. So if we see signs of life with these 100 samples, we can presumably like make a much larger training run after that, right?
Totally. And probably get even better results.
Nice.
All right, so now that we've created those 150 samples and sampled them, we can check out the distribution of them, where I forgot one cell, just this one. Exactly. We're counting the frequency of all of them, and we are going to be plotting their distribution. And as you can see here, that's the distribution across all the categories and the number of times we see them in the transcript. Does that look good to you, Prashant?
I mean, it's definitely a distribution. What are we looking for here? Would we want to sort of have an equal number of occurrences of each of these labels, or
Yeah, so ideally, it would be equal distribution for all of the categories. And the reason is that if we train the model with this type of imbalanced data set, it's going to artificially increase the score by only predicting trade or agri-food stuff.
I see.
And therefore, it will not be able to generalize across all the categories. But we want a more general model.
Is this what they mean by reward hacking?
A version of it, yeah.
Hey everyone, welcome back to another Build Hour. I'm Christine, I'm on the startup marketing team, and today I'm here with Will and Theo.
Hey, I'm Will. I'm on the engineering team building the fine-tuning product.
Yeah, and I'm Theo, solutions architect, working with Star.
Formatting errors, like writing out 32 to interact with the outside world.
There below, and we'll keep adding them. So thanks everyone, and we'll see you next time.
at Google, and my work has been mainly around application modernization and emerging technologies. I'm an active conference speaker, and generally I've been speaking around Kubernetes, platform, distributed systems, and DevOps SRE landscapes. As I mentioned, today's session is going to focus on GK Inference Gateway. This is a recent addition to the GK stack. And in case you have any questions, feel free to chime in or probably raise your hand or write on the chat box. Siddhi will be helping us moderate the session. If we
Despite the fact that I was involved in inventing the transformer, luckily, no one's been working on them as long as I have, right? With maybe the exception of the other 7. Despite the fact that I was involved in inventing the transformer, luckily, no one's been working on them as long as I have, right? With maybe the exception of the other 7 authors. So I actually made the decision earlier this year that I'm going to drastically reduce the amount of research that I'm doing specifically on the transformer because of the feeling that I have that it's an oversaturated space, right? It's not that there's no more interesting things to be done with them, and I'm going to make use of the opportunity to do something different, right? To actually turn up the amount of exploration that I'm doing in my research.
We just released the Continuous Thought Machine. It's a spotlight at NeurIPS 2025 this year. You should care about it because it has native adaptive compute. It's a new way of building a recurrent model that uses higher level concepts for neurons and a synchronization as a representation that lets us solve problems in ways that seem more human by being biologically and nature inspired.
The atmosphere in AI research was actually quite different back during the transformer years, because it doesn't feel like something similar could actually happen right now because of the reduced amount of freedom that we have, right? The transformers was very, very bottom up. Right? It's not that somebody had this grand plan that came down from on high that this is what we should be working on. It was a bunch of people talking over lunch, thinking about what the current problems are and how to solve them, and having the freedom to have, literally months to dedicate to just trying this idea and having this new architecture fly out. We've spent hundreds of millions of dollars. The biggest sort of evolution-based search is probably in the tens of thousands. We have all this compute. What happens? What happens if you scale up these search algorithms? And I'm sure you'll find something interesting, when someone eventually does bite that bullet and really scale up these evolutionary sort of A-life experiments. Because I pitched it in an environment where people were just going all in on this one technology, I got zero interest. So now, I have my own company, and I can pursue those directions.
This podcast is supported by Cyberfund.
Hey folks, I'm Amar, product and design lead at Google DeepMind. We just launched a revamped vibe coding experience in AI Studio that lets you mix and match AI capabilities to turn your ideas into reality faster than ever. Just describe your app, and Gemini will automatically wire up the right models and APIs for you. And if you need a spark, hit I'm feeling lucky, and we'll help you get started. Head to ai.studio/build to create your first app.
2 for AI Labs is a research lab based in Zurich. They've got a team of amazing ML engineers and research scientists. They're doing some really cool stuff. If you look at their website, for example, you can see what their approach for winning the ARC AGI 3 pub competition, which closed out a few months ago. And they are hiring amazing ML engineers and research scientists. They also care deeply about AI safety. So if any of that is a fit for you, please go to 2 for AI Labs and give it a go. The audience will know I'm a huge fan of Kenneth Stanley's ideas. So his book, Why Greatness Cannot Be Planned, changed my life. It was absolutely insane. And what he was speaking to is that we need to allow people to follow their own gradient of interest, unfettered by objectives and committees and so on, because that is how we do epistemic foraging. That when you have too many agendas involved in the mix, you kind of end up with a grey goo, and you don't discover, interesting novelty and diversity. And I suppose that's basically the thesis of your company, Sakana, is to lean into those ideas.
Yes, exactly. At the company, we're a massive fan of that book. We're hoping to have him come and talk at our company next week, actually. And it's a philosophy that we do talk about internally, right? We have copies of the books, including the recent Japanese translation. As one of the co-founders, one of my main jobs, one of the main things that I have to keep doing for this company is making sure that we protect the freedom that the researchers currently have, right? Because it's a privilege, really, that we have the resources to be able to do that. And inevitably, as I've seen happen, as the company grows, more and more pressure comes in and it narrows the freedom. But I think because we believe in this philosophy so strongly, I'm hoping that we can give people all the research freedom that we do now for as long as possible.
And what are those processes that curtail freedom as a company matures? I mean, how would you describe that?
It's great that there's never been so much interest and people and talent and resources and money in the industry. But unfortunately, that just increases the amount of pressure people have in order to compete with all the other people working on it and trying to get the value out of this technology and making money. And I think that's what just happens. Like, as a startup, you have a feeling of excitement and trying something new. And right at the beginning, you have a bit of a runway, so you have the freedom to try different things. But inevitably, people are starting to ask for returns on their investments, or they're expecting you to churn out some product. And this just unfortunately reduces the creativity that researchers have, because the pressure to publish or the pressure to create technology that's actually useful for the products that we have goes up. And so the feeling of autonomy, I think, starts to go down. But I literally tell people when they start working for the company, I want you to work on what you think is interesting and important, and I mean it.
There is, in YouTube, there's a phenomenon called audience capture.
Right.
And I think there might be a phenomenon called technology capture, which is that in the early days of Google, it was quite open-ended. And Transformers is now the ubiquitous backbone of all AI technology, and it's a huge achievement that you're involved in that. But there's a similar story with OpenAI. They're now starting to see all of these commercialization opportunities. They're going to become LinkedIn. They're going to become an application platform. They're going to become a search platform. They're going to become a social network. And I guess this could happen to you guys. That there's a very strong chance, especially with your new paper that we're going to talk about today, this continuous thought machines. It could be a revolutionary technology, but then it will become obvious how it could be commercialized. And that's how those pressures come in.
I like that. I like the audience capture analogy. I think there's definitely been some kind of capture by large language models, right? They worked so well that everyone wanted to work on them. And I'm really worried that we're kind of stuck in this local minimum now, right? And we sort of need to try to escape it. So we spoke about the Transformers, but there's a time just before the Transformers that I'd like to talk about because I think it's quite illustrative. So of course, the main technology before Transformers was recurrent neural networks, right? And there was a similar feeling, right? When recurrent neural networks came in and we discovered this new sort of sequence-to-sequence learning, that was also a massive breakthrough, right? The translation quality went up massively, right? Voice recognition quality went up massively. And there was a similar sort of feeling then of like, okay, yes, we found the technology and we just need to sort of perfect this technology. And back then even, my favorite task was character level language modeling, right? So every time a new RNN-based character level language modeling paper came out, I got quite excited, right? I wanted to quickly read the paper, like, okay, how did they get the improvements? But the papers were always these slight modifications on the same architecture, right? So it was LSTMs and GRUs and maybe initializing it with the identity matrix so you could use the ReLU function, or like maybe if you put the gate in a different place, or if you layered them in a slightly different way, or if you had gating going upwards as well as sideways. And I remember one of my favorites was this like hierarchical LSTM, where it would actually decide to compute or not compute at the different layers. And if you trained on Wikipedia and you looked at the structure of when it was decided to compute or not compute, it kind of looked like the structure of the sentences were actually being picked up by the model. And I used to love that sort of stuff, right? But the improvements were always like 1.26 bits per character, 1.25 bits per character, 1.24. That was the result. That was publishable, right? That was exciting. But then after Transformer, the team that I went on to afterwards, right, we applied for the first time very deep transformer models, decoder transformer models to language modeling, and we immediately got something like 1.1. But so something that was so good that people actually come to our desk and politely tell us, like, I think you made an error, like a calculation. Do you think it's nats, not bits per character? And we're like, no, it really is the correct number. What struck me later is that all of a sudden, all of that research, and to be clear, very good research, was suddenly made completely redundant.
Yes.
Right? All of those endless permutations to RNNs were suddenly seemingly a waste of time. We're kind of in a situation right now where a lot of the papers are just taking the same architecture and making these endless amount of different tweaks of, like, ways to put the normalization layer and slightly different ways of training them. And we might be wasting the time in exactly the same way, right? Like, I personally don't think we're done. Right? I don't think that this is the final architecture and we just need to keep scaling up. There's some breakthrough that will occur at some point. And then it'll once again become obvious that we're kind of wasting a lot of time right now.
Yeah, so we are a victim of our own success. And this basin of attraction, there are so many basins of attraction. Sarah Hooker spoke about the hardware lottery, and this is a kind of architecture lottery. And it actually made me think of the agricultural revolution, which is that this kind of phase change happened, and all of the folks that had these skills that were so necessary, these diverse skills for living and surviving, they died out. And that's actually quite paradoxical, because we need those skills to take the next step. And so we're now in this regime. We've got the term foundation model. And the implication is that you can do anything with a foundation model. In the corporate world, we used to have data scientists. There were ML engineers doing these architectural tweaks, even in mid-sized enterprise. And now we just have AI engineers who are just doing prompt engineering and so on. So you're saying that the fundamental skills that we need to be diverse, to think of new solutions and new architectures, they're dying out.
I think I'm going to disagree with that. I think the problem is we have plenty of very talented, very creative researchers out there, but they're not using their talent, right? For example, if you're in academia, there's pressure to publish, right? And if there's pressure to publish, you think to yourself, okay, well, I have this really cool idea. but it might not work. It might be too weird, right? It might be difficult to get it accepted because I have to sort of like sell the idea more. Or I can just try this new position embedding, right? The problem is that the current environment, both in academia and in companies, are not actually giving people the freedom that they need to do the research that they probably want to do.
I mean, there's also this interesting thing that even in spite of great new research, I mean, I was speaking to Sepp Hopwriter, and he's got all of these new architecture ideas, and OpenAI aren't implementing them. I mean, Google are doing this diffusion language model, which is quite cool. And I'd like to know your opinion on why that is. So there's a few philosophies floating around, like this concept of a universal representation, that there are universal patterns, and the transformer representations resemble those in the brain. And it's rather led to this idea of, we don't need to use different architectures, because if we just have more scale and more compute, then all roads lead to Rome, so why would we bother doing it any differently?
There's actually better, right? There is actually already architectures that have been shown in the research to work better than transformers, okay? But not better enough. Move the entire industry away from such an established architecture where you're familiar with it, you know how to train it, you know how it works, you know how the internals work, right? You know how to fine-tune them. You have all this software is already set up for training transformers, fine-tuning transformers, inference. So if you want to move the industry away from that, being better is not good enough. It has to be obviously crushingly better. Transformers were that much better over RNNs. Okay, transformers where you just applied it to a new problem and it just was so much faster to train and you just got such higher accuracy that you just had to move. And I think the deep learning revolution is also another example of that, right? Where you had plenty of skeptics and people were pushing out neural networks even back then. And people are going, no, we think symbolic stuff will work better. But then they demonstrated it as being so much better that you couldn't ignore it. This fact makes finding the next thing even harder, right? That's the gravitational pull of always pulling you back to, oh, okay, but the transformer's good enough. And yeah, you made a cool little architecture over here that, yeah, it looks like it's got better accuracy, but OpenAI over here just made it 10 times bigger and it beats that. So let's just keep going.
May I also submit that there could be an additional reason, which is, I love that fractured entangled representations paper. There's this shortcut learning problem. And I think that there's a little bit of a mirage going on here. And there might be problems with these language models that we don't, that we're not fully aware of. And there's also this thing that we're seeing that we are starting to bastardize the architecture. So we know we need to have adaptive computation for reasoning. We know we want things like uncertainty quantification. And what we're doing is we're bolting these things on top rather than having an architecture which intrinsically does all of these things that we know we need.
Yeah, and I think our continuous thought machine is an attempt at addressing those more directly, right? Which Luke will be able to tell you more about later. There's something still not quite right with the current technology, right? I think the phrase that's becoming popular is jagged intelligence, right? That the fact that you can ask an LLM something and it can solve literally like a PhD level problem, and then in the next sentence it can say something just so clearly, obviously wrong that it's jarring, right? And I think this is actually a reflection of something probably quite fundamentally wrong with the current architecture. As amazing as they are, the current technology is actually too good. Okay, another reason why it's difficult to move away from them, right? So they're too good in the following sense. And you spoke about the fact that we have these foundation models. It's okay, so that we have the foundation, we can do anything with them. Yes, I think current neural networks are so powerful that if you have enough patience and enough compute and enough data, you can make them do anything. But I don't necessarily think that they want to, right? We're sort of forcing them, but they're universal approximators. But I think there are probably a space of function approximaters that will more want to represent things in the way that a human represents them. So there's actually quite an obscure paper that is my poster child for this. It's called Intelligence Matrix Exponentiation. And I think it was actually rejected. So, you can probably project the image of a figure 1, but there's an image of it solving, the classical spiral data set of needing to separate the two classes in the spiral. Yes. And it has the decision boundary for both a classic RNN multilayer perceptron and a tanh multilayer perceptron. And you can see they both solve it, right? Technically, they both solve the problem because they classify all the points correctly and get a very good test score on this very simple data set. And then they show you the decision boundary for the M layer that they built in this paper. And it's a spiral. The layer represented the spiral as a spiral. Shouldn't we? If the data is a spiral, shouldn't we represent it as a spiral? And then if you look back at the decision boundaries for the spiral in the classic ReLU multilayer perceptron, it's clear that you just have these tiny little piecewise linear separations. And that's what I mean. Yes, if you train these things enough and you push these little piecewise linear boundaries around enough, it can fit the spiral and get a high accuracy. But there's no feeling when I look at that image that the ReLU version actually understands that it is a spiral. Right? And when you represent it as a spiral, it actually extrapolates correctly because the spiral just keeps going out.
You're touching on something fascinating there, because we were talking about the need for adaptivity and adaptive computation. I'm really inspired by Randall Balestriero's spline theory of neural networks, and we've had them on many times. And you can look on the TensorFlow playground. You can look what happens when you have a ReLU network on this spiral manifold. And you'd be forgiven for thinking that these things are basically a locality-sensitive hashing table, right? Because they partition the space and they can predict the spiral manifold, right? But we want to do something a little bit more different than that. And it also comes into this imposters thing, because just tracing the spiral manifold, but not continuing the pattern, there's a big difference between that. Yes. So from an imposter perspective, just tracing the pattern is not learning it abstractly or constructively, right? If we learned it constructively, so you speak about this in your paper, this complexification, the abstract building blocks, and you can do adaptive computation, you understand the spiral. That means that with adaptive computation, you can continue the spiral, and then you can update the model's weight so it has adaptivity, because that's so important for intelligence. So we know that we need models that can do these things, but for some reason, they're so sycophantic that they're almost better than an adaptive intelligence system, because they tell us exactly what we want to hear. They seem so intelligent, but we know that they're missing these fundamental properties.
I'm still fairly skeptical when I see video generation models. We went through a phase where you could detect them because of the number of fingers on somebody's hand, right? And yes, with more data, with more compute, with better training tricks, okay, they submit, and now they usually do have 5 fingers. But did we fix the problem? Or did we just use more brute force to just, force the neural network to know it's 5 fingers, where something that actually had a much better kind of representation space? It's almost mad that it's controversial to say that we should represent a spiral like a spiral, but, something that could do that generally human hand the way that, maybe I represent a human hand, then maybe it would be much easier to count how many fingers are on a hand. It's unfortunate that they work so well. It's unfortunate that scaling works so well because it's too easy for people to just sweep these problems under the carpet.
You guys have possibly created what I think might be the best paper of the year. This could actually be the innovation which takes us to the next step. And did you get the spotlight in Europe as well?
Yeah.
This year? And congratulations on that. So I think that's testament to how amazing this paper is.
The CTM, the continuous thought machine, it's actually not that far outside of the local minimum that we're stuck in, right? It's not as if we went and found a completely new technology, right? We took quite a simple biologically inspired idea, right, of the fact that neurons synchronize, and not even necessarily in a biologically plausible way, right? Brains don't literally have all the neurons wired together in a way that they work out the synchronization. But it's the sort of research that I want to encourage people to do, and the way to sell it is quite easy, I think. At no point did we have to worry about being scooped, right? That stress was taken away from us completely. So there was no pressure to sort of rush out with this idea because there's probably somebody else working on exactly this. And I think the reason that we were able to get a spotlight is because we were able to create such a polished paper. We took the time to do the science properly, to get the baselines that we wanted and do all the tasks that we wanted to try. Encouraging researchers to take a little bit more of a risk, right, to try these slightly more speculative long-term ideas, I think is the sad thing is I don't think it's necessarily a very difficult thing to sell. And I want to have the CTM as like a poster child of it works, right? It was a bit of a risk. We didn't know if we were going to find something interesting, but it was our first shot and we did find something interesting and it became a successful paper.
If we do find a system which can acquire knowledge, design new architectures, do the open-ended type of science that you're speaking to, can you see a future where at some point the locus of progress will be mostly driven by the models themselves?
I think so. Whether or not that's going to replace us completely, I go back and forth on. Powerful algorithms are helping us do research, right? And I think it might just end up being a more powerful version of that. Right? I know the AI scientists that we released, we showed that you could actually go end to end, right? Go from seeding the system with an idea for a research paper and then just take your hands off and just let it go. Think about the idea, write the code, run the code, collect the results, and write the paper to the point that we were actually able to get it to a 100% AI-generated paper accepted to a workshop recently, right? But I think we did that to show that you could do it, right, as a sort of demonstration. In a real system, I think I would want it to be much more interactive, right? I would want to be able to seed it with an idea and then have it come back with more ideas, have a discussion with me, then go away to write code. I want to look at the code and check it, and then discuss the results as they're coming out. So that's the sort of near-term future that I would envision, well, how I would like to do research with an AI.
And could you introspect on that? Is it because you feel we need supervision because the models don't yet understand? There's this path dependence idea. So we need to do supervision because we have the path dependence, so we can guide the generation of the language models. Maybe in the future the language models will just understand better themselves. But there's also the output dimension, which is that we want to produce artifacts that extend the phylogeny of human interest. We want it to be human relevant.
Yeah, I think it's more that, in that initial seed idea, it's probably impossible to actually describe exactly what you want. It's exactly the same with, when I have an intern. I can't just have an intern come into the company and I go, I have this mad idea, and then just explain it to them and then just leave them alone for 4 months. There's a back and forth because I have a particular idea that I want to explore and I need to keep steering them in the direction that I had in my mind originally. So I think it's more.
You have such a deep understanding. So you have this rich provenance and history and path dependence. And that means you can take creative steps. Intuitive steps for you respect the phylogeny. They respect all of this deep abstract understanding that you have. And interns don't yet have that. Right. But maybe AI models in the future will have that.
Yeah, sure. If they get to the point where my inputs becomes detrimental, then yeah, that'll be a thing. It's kind of like chess, right? There was a point at which chess engine and human fusion actually beat chess engines. That's not true anymore, right? Adding a human into the mix actually makes the bots worse.
Oh, interesting. I wasn't aware of that.
Yeah. So what to do when that day comes for AI scientists is a broader discussion, I think.
I think now is a good segue to talk about this paper in a little bit more detail. So this continuous thought machine, you were just pointing to it before. Luke, first of all, mate, introduce yourself and set this thing up for us.
My name's Luke. I am a research scientist at Sakana AI, and my primary sector of research is this continuous thought machines. It took us somewhere in the region of about 8 months working on this project with the whole team. I did a lot of work, but we also had a lot of people in different areas and doing different parts of it. That I think an 8-month life cycle for a paper seems a bit long for AI research at the moment. But yes, to the actual technical points of the paper. So we call it continuous thought machines. It originally had a different name. We called it asynchronous thought machines before, but every single time people asked us what's the asynchronous part, it became a bit confusing. So continuous thought machines basically depends on 3 novelties. The first one is having what we call an internal thoughts dimension. And this is not necessarily something new. It's related conceptually to the ideas of latent reasoning. And it's essentially applying compute in a sequential dimension. And when you start thinking about ideas and problems in this domain and in this framework, you start understanding that many problems that look like or solutions to problems that look intelligent are often solutions that have a sequential nature. So for instance, one of the primary tasks that we tested in the continuous thought machines was this maze solving task. And solving mazes for deep learning is quite trivial. It's really easy to do if you make the task easy for machines. And one of the ways to do this is you give an image of a maze to a neural network, like a convolutional neural network, and it outputs a image, same size of the maze, and it's zeros where there isn't a path, and there's ones where there is a path. There's some really brilliant work showing how you can train these in a careful way and scale them up essentially indefinitely. And this is fascinating. Really interesting idea of how to solve this. However, when you take that approach out of the picture and you ask what is a more human way to solve this problem, it becomes a sequential problem. You have to say, well, go up, go right, go up, go left, whatever the case may be, to trace a route from start to finish. And when you constrain that simple problem space and you ask a machine learning system to solve it like that, it turns out to actually get much, much more challenging. So this became our hello world problem for the CTM. And applying an internal sequential thought dimension to this is how we went about solving this. 2 other novelties that we can touch on and talk about. We sort of rethought the idea of what neurons should be. There's a lot of excellent research in this world in cognitive neuroscience, particularly exploring how neurons work in biological systems. And then we get on the other side of the scale how deep learning neurons work, which the quintessential example is ReLU. It's off or on in a sense. And this very, very high level abstraction of neurons in the brains feels a little bit myopic. So we approached this problem and said, well, let's on a neuron by neuron basis, let this neuron be a little model itself. And this ended up doing a lot of interesting work on how to build dynamics in the system. The third novelty here is, as I said before, we have this internal dimension over which thinking happens. We ask the question, well, what is the representation? What is the representation for a biological system when it's thinking? Is it just the state of the neurons at any given time? Does that capture a thought, if you wish, if I can be controversial and use the term thinking and thought? And my philosophy with this is no, it doesn't. That the concept of a thought is something that exists over time. So how do we capture that in engineering speak? We, instead of measuring the states of the model that is recurrent, we measure how it synchronizes, how neurons synchronize in pairs along with other neurons. And this opens up the door to a huge array of things we can do with this type of representation.
You were talking about this sort of sequential nature of reasoning. And devil's advocate, I mean, there was that Anthropic biology paper, and they were talking about planning and thinking, and they were saying that this thing is planning ahead, because I think your system actually, we can say, does planning. It's actually different computationally. Can you explain that?
Yes, I think the boundary in terms of computation from a Turing machine perspective, if you wish, is really interesting, because the notion of being able to write your tape, read from the tape, and then write again to be in a Turing complete system is obviously an incredible idea that has completely changed the world. And I think the primary difference with, let's talk about transformers versus what we're trying to do with the CTM, is that the process that the CTM thinks in, we can apply that process, that internal process, to breaking down a problem. So the problem itself can be there is a single solution to this problem. And you could do that in one shot. You could, as I explained with the maze, you could just process that in one shot. But there are certain phrasings of problems that are real problems that doing so becomes exponentially more challenging. So in the maze task, a really good example is that if you try to predict 100, 200 steps down the path in one shot, no models that we could train, not even our model could do that. And we needed to actually build an auto-curriculum system where the model first predicted the first step, and then when it could predict the first step, then we started training it on the second and third and fourth step. And the sort of resulting behavior of this is where it gets interesting. One of the ways that I like to do research, and that I encourage people who work with me to do research, is understand if you wish, the behavior of a model. We are getting to a point now where the models that we build are demonstrably intelligent in ways that keep surprising us. And breaking that down into a single set of metrics, or even a finite single metric about performance, seems maybe not to be the right way to do it for me. And understanding the behavior and the actions that those models take when you put them in a system and train them in a certain way seems to reveal more about what's actually going on under the hood.
Very cool. And I think I didn't pick up on this. So you're doing a fixed number of steps. So you have like a context window. And did you say that you set that around 100 steps?
So for the maze task, the model always observes the full image at every step. The CTM will observe the full image. For argument's sake, those images could be tokens from a language, the output of a language model. Those inputs could be numbers that the model has to sort, whatever the case may be. It should be agnostic to data. That's how we try to build it. But in the maze task, the model can continuously just observe the data. No matter where, it can look at the whole image simultaneously, but it uses attention to retrieve information from the data. And it has, let's call it 100 steps that it can think through. And what we do is we pick up, at some point the model solves 3 steps through the maze. So it says I'm going to go up, and right, and then it's correct, but then it makes a wrong turn. And at that point we stop supervision. We only train it to solve the 4th step. So one more than what it could. In practice we would 5, but the principle holds. And when you do that, it's a self-bootstrapping mechanism. And I think the intuitive listener will understand how that extends to other domains, other sequential domains, for instance, like language prediction, many tokens ahead, that sort of thing.
So I'm really interested in this idea of adaptive computation. So I guess the first question is, how sensitive was the performance to the number of steps? And then the next question would be, could you have an arbitrary number of steps, which means that, perhaps based on uncertainty or, some kind of criterion, you could do fewer steps. And then the final question is, could you have potentially like an arbitrary or unbounded number of steps?
Yeah, really super question. I think that I'll answer the uncertainty question first about the sensitivity to steps. So a very good example of this is we just train the model on ImageNet classification. And our loss function is quite simple. What we do is we run it for example, 50 steps. And we pick up 2 points, 2 distinct points. The first one is where is it performing the best, i.e. where is the last and lowest. And the second one is where is it most sure, or where is it most certain. And those give us 2 indices, between 0 and 49 inclusive. And we apply cross entropy at both of those points. We just make the loss the average of the cross entropy at those points. So what this does is it induces a behavior where easy examples are solved almost immediately in 1 or 2 steps, whereas more challenging examples will naturally take more thinking. And it enables the model to use the full breadth of time that it has available to it, just in a natural fashion without having to force it to happen.
So you've decided to model every neuron as an MLP, which is really fascinating to talk about that, but also there's this notion of synchronization. And I think you use the inner product to determine the extent to which the parameters are synchronized, and this kind of unfurls over time as the driving force. Can you explain that in a bit more detail?
Absolutely. I think it's a good point to explain the neuron level models, as we call them in the paper, or NLMs, first, because it ties into this. So you can imagine a recurrent system is a state vector that is being updated from step to step. We track that state vector, and that state vector unfolds, and for each individual neuron, each I neuron in the system, we have a unfolding time series. It's a continuous time series. Well, it's discrete, but it's a continuous value. And those time series define what we call the activations over time. And synchronization is quite simply just measuring the dot product between 2 of these time series. So you have a system of D neurons, and essentially you have D over 2 squared different synchronization pairs. So neuron 1 can be related to neuron 2 by how they synchronize, and neuron 1 can also be related to neuron 3, etc., etc. The neuron level models, they function by taking in a finite history, like a FIFO queue of activations coming in, and instead of being just a rate of activation, they use that history as information to process a single activation out. And that is what moves from what we call pre-activations to post-activations. And the principle here is that this might seem rather arbitrary, and does it help for performance? It turns out it does, but that's not really the catch-all solution here. That's not what we're after. What we're after here is trying to do something biologically plausible. Find the line somewhere between biology, which is how the brain implements things in the biological substrate that we have, versus deep learning, which is highly parallelizable, super fast to learn, backprop amenable, all of the nice properties of that have got us this far. And find a line somewhere where we can take some sprinkling of biological inspiration, but still train it with deep learning. And it turns out that neuron level models is a nice interim that we can do this with. The concept of synchronization is applied on top of the outputs of those neuron level models.
So on the scaling, I think the time complexity is quadratic in respect of the dimension of the synchronization matrix, right? And in your paper, you were talking about subsampling to improve the performance, but how did that affect the stability and were there any things that cost you doing that?
Yeah, it's a neat question. I think in terms of stability, what we found was kind of fun, and this was a sentiment that we had throughout the experiments that we ran in this paper, was it tended, no matter what we tried it on, it just kind of worked with all spreads of hyperparameters. And the problems that you have with backprop through time, typically with recurrent models like RNNs and LSTMs, it's a challenge. And you run for many internal ticks with the RNNs or the LSTMs, and the learning seems to break down. But the fact that we use synchronization in some sense touches all of the neurons through all of the time. So it really helps with gradient propagation. A nice interesting point that's maybe a bit oblique to what you asked about synchronization is we have a system of D neurons, and like I said earlier, there are D over 2 squared possible combinations. This essentially means that our underlying state or underlying representation to the system is quite a lot larger than what you would get with just taking those D neurons. And as to what that means in terms of downstream computation and performance and the things that we can do with this is what we're actively exploring right now.
You guys used an exponential decay rate?
You have the system that unfolds over time. It would be maybe a little bit too constrained if the synchronization between any two neurons depended on the same time scale. So for instance, there are neurons in your brain that are firing over very long time scales and very short time scales. The way that they fire together impacts other neurons and causes those neurons to fire. But everything in biological brains happens at diverse time scales. That's why we have different brain waves for different thinking states, for instance. But beside that point, what we do with the exponential decay in the continuous thought machines is it allows us for a very sharp decay to say that these two neurons that are pairing together, what only really matters is how they fire together right now. Right? But if we had a very long and slow decay, essentially that's capturing a global sense of how those neurons are firing over an extremely long period of time. So this was essentially a way of us capturing this idea of how different neurons can maybe fire together very quickly and other neurons can fire together very slowly or not at all. And this lets that representation space that I spoke about, that d over 2 squared representation space, lets it again become more rich. And we can enrich that space with more subtle tweaks to how we compute those representations.
So we were speaking about this yesterday, Luke, that when folks apply transformers to things like the ARC challenge or things that need reasoning, we need to do lots of domain-specific hacks. So the architects who were the winners of last year's challenge, they did depth-first search sampling, and some folks have been experimenting with using language representations or using DSLs. And some part of this is to do with the reachability of language, right? And language is quite dense, which means you can kind of monotonically increase. But if I understand correctly, your system might have some interesting properties for reasoning and for discrete and sparse domains, and also for sample efficiency, because we want to build a system that can actually do well on things like the ARC challenge. But can you kind of explain in simple terms why you think this architecture could be significantly better than transformers for doing those things?
I think a lot of the really fascinating work in the last few years that I found fascinating in the literature of language models has been related to what one can actually call a new scaling dimension. I, in some sense, see chain of thought reasoning as a way of adding more compute to a system. That's obviously just one small part of what it really is and what it really means, but I think it's quite a profound breakthrough in some sense. Now, what we're trying to do is have that reasoning components be entirely internal, yet still running in some sort of sequential manner. And I think that that's rather important. And you spoke earlier about Gemini's diffusion language modeling. And I think there are a lot of different directions that are exploring this right now. I do think that the continuous thought machine with the ideas of synchronization and multi-hierarchical temporal representations gives a certain flexibility on that space that other people are not yet exploring, and that richness of that space being able to project the next step to solve the ARC challenge, and the next 100, the next 200 steps, to be able to break that down into a process that a model can then very quickly search that process in its high-dimensional latent space, becomes something that feels like a good approach to take.
Do you see any relationship between this architecture and Alex Rave's neural Turing machine?
Yes, that's really interesting. I do. I think that one of the most challenging parts about working with a neural Turing machine is the concept of writing to memory and reading to memory, because it is a discrete action, and that has its own challenges associated with it. And yes, I wouldn't go so far as to say that the continuous thought machine is definitively Turing complete, but the notion of doing reasoning in a space that is latent and letting that space unfold in a way that is rich towards a different set of tasks. And this actually brings me to a point that I find quite interesting, that I'd like to share with you. Consider again the image test or any sort of classification task. It's a nice test bed. There are many images that are really easy, and there are many images that are really difficult. When we train, for instance, a VIT or a CNN to do the task, it has to nest all of that reasoning in the same space. It has to put all of its decision-making process for a very simple, obvious cat versus some complex, weird, underrepresented class in that data set. And it has to nest it all in parallel in a way that is, we get to the last layer and then we classify. I think breaking that down, where you have different points in time where you can say, now I'm done, I can stop, versus now I'm done, I can stop, lets you take a data set or take a task and actually naturally segment it into its easy to difficult components. And I think we know that curriculum learning and learning in this continuous sense, again, seems to be a good idea. It's how humans learn. And if we can get at that architecturally and just have that fall out in the model, again, this seems like something worth exploring. I'm not sure if you know much about model calibration and how neural networks tend to be poorly calibrated.
Go for it, tell me.
It's a bit of an old finding, but if you train a neural network for long enough and it fits really, really well and you've regularized it networks tend to be poorly calibrated.
Go for it, tell me.
It's a bit of an old finding, but if you train a neural network for long enough and it fits really, really well and you've regularized it really, really well, you'll find that the model is uncalibrated, which essentially means that it is very certain about some components some classes where it's wrong and uncertain for some classes where it's correct. Essentially, what you want for a perfectly calibrated model is if it predicts a probability that is in class, the correct class, with 50%, 50% of the time you want it to be correct about that class, and so on and so forth. So a well-calibrated model, if it's predicting a probability of 0.9 that it is a cat, then 90% of the time it should be correct. And it actually turns out that most models that you train for long enough get poorly calibrated. And there are loads of post hoc tricks to fixing this. We measured the calibration of the CTM after training, and it was nearly perfectly calibrated, which is again a little bit of a smoking gun that this actually seems to be probably a better way to do things.
The flavor of this kind of research is such that we didn't actually go out and actually try to create a very well calibrated model, right? And we didn't even try to create a model that was necessarily going to be able to do some kind of adaptive computation time, right? I was a very big fan of the paper, adaptive computation time, was Alex Graves, was it? But that paper, it had a massive amount of hyperparameter sweeps in it, because in that paper, he needed to have a loss on the amount of computation that was being done. Yeah. Because anytime you try to do some sort of adaptive computation time research, what you're fighting is the fact that neural networks are greedy, right? Because obviously the way to get the lowest loss is to use all the computation that you have access to. So unless you had like an extra loss that had a penalty that said, okay, actually you're not allowed to use all the computation, that's, and very, very carefully balanced loss, that's when you actually got the interesting dynamic computation time behavior falling out of the model in that paper. What was really gratifying to see with the continuous thought machine is that because of the way that we set up the loss that Luke described earlier, adaptive computation time seems to just fall out naturally. So that's more the way that I think research should go, okay? Because we don't actually have like a specific goal, or like a specific problem we're trying to fix like that, or something we're trying to invent. It's more that we have this interesting architecture and that we're just following the gradients of interestingness.
Yes, and on that point, I think maybe the most exciting thing about your paper is, we were talking about path dependence and having this understanding which is built step by step, this process of complexification. And I mean, maybe this is apropos in the theme of world models in general, and also active inference. And I say active inference in big quotes because it's not Carl Friston's active, maybe adaptive inference or something like that. We want to build agents that can continue to learn, that can update their parameters, and most importantly, can construct path-dependent understanding. And because that's completely different to just understanding what the thing is, it's how you got there is very important. And this architecture potentially allows these agents using this algorithm to explore trajectories in spaces, find the best trajectories, and actually construct an understanding which carves the world up by the joints.
Yeah, that's a really neat perspective. I haven't actually thought about it like that. But yes, I think that particular stance becomes really interesting when you think about ambiguous problems, because carving the world up in one way is as performant as carving it up in another way.
Yeah.
Perhaps the hallucination in language models is carving the world up in some fine way, but it's just not performance in our measure of this is hallucination, and actually that's not true. But in some other trace down the path of wanting to carve the world up through a autoregressive generation of tokens, you end up in a different carve up of that world. And being able to train a model that can be implicitly aware of the fact that it is actually carving up the world in a different way and can explore those manners, those descents down the carve up, is something that we're often. I think it's quite an exciting approach to be trying to take a stance of let's break up this problem into small solvable parts and learn to do it like that. And how can we do this in a natural way without too many hacks?
Yeah, it's something I've been thinking about because Cholet, as much as I love his measure of intelligence ideas, is for him adapting to novelty is getting the right answer. And the reason why you gave that answer is very, very important. And in machine learning, we have this problem that we come up with this kind of cost function. That rather leads to this shortcut problem. But we could just build a symbolic system. We could be Go-Fi pilled and we could say, okay, we need to do this principled kind of construction of knowledge maintaining semantics. Well, we're not doing that. We're doing a hybrid system. But there must be some natural way of doing reasoning where, in spite of the end objective being this cost function, that because of the way that we traverse these open-ended spaces, that we can actually have more confidence mechanistically that we're doing reasoning which is aligned to the world.
I think that's a great way of seeing this particular avenue of research. And I think that obviously we're not the only people thinking like this, and we're not the only ones trying to do this. What we have is an architecture that's amenable to it. And surprisingly so, it wasn't the goal. It's not the goal to do this type of research. It's not the goal to be able to break the world down into these small chunks that we can actually reason over in a way that seems natural. Instead, what we did was pay respect to the brain, pay respect to nature, and say, well, if we build these inspired things, what actually happens? What different ways of approaching a problem emerge? And then when those different ways of approaching a problem emerge, what big philosophical and intelligence-based questions can we then start to ask? And that's where we're at right now. So it might feel at times, especially for me, too many questions and too few hands to answer those questions. But I think the fun and exciting thing and the encouraging thing that I can try to encourage other younger researchers out there is that do what you're passionate about and figure out how to build the things that you care about, and then see what that does, see what doors that opens up, and see how to explore deeper into those domains.
We were talking about this yesterday, weren't we? That you can think of language as being a kind of maze.
Yes.
Like, what is to stop us from taking this architecture and building the next generation language model with it?
I mean, that's honestly, as you know, something that I am actively trying to explore right now. And I think the maze task gets really interesting when you add ambiguity to it, when there are many ways to solve the maze. Honestly, this isn't something I've tried yet, and maybe it's something I should try next week. But it's essentially, you can imagine an agent or CTM in this case observing the maze and taking a trajectory. And surprisingly, we saw this. We have a section in our recently updated paper on arXiv, the final camera-ready version of this paper, where we added an extra supplementary section that is not in the main technical report. And that supplementary section is basically, hey, we saw this cool stuff happen. And we list, I think, 14 different interesting things that happened while we were doing the research that obviously didn't make it into the paper, but we wanted people to know about these strange things that happen. And this is one of the strange things, where we watched during training what was happening. And at some time during training, maybe halfway through the training run, we could see what the model would do is it would start going one path in the maze, and then suddenly it would realize, oh no, damn, I'm wrong, and would backtrack and then take another path. But eventually it gets really good, and it does some sort of distributed learning in this because it's got a attention mechanism with multiple heads, so it can actually just figure out how to do this pretty well and refine its solution. But sometime early on in the learning, it descends multiple paths and comes back and backtracks. We have a really fascinating set of experiments that also show, and this we actually have some supplementary material online showing this, where, and I don't really know what to say, it's kind of a deep philosophical thing, but if you're trying to solve a maze but you don't have enough time, it turns out that there's a faster algorithm to do it. And this blew my mind when I saw it. So if we constrain the amount of thinking time that the model has, but still get it to try to solve a long maze, instead of tracing out that maze, what it does is it quickly jumps ahead to approximately where it needs to be, and it traces backwards, and it fills in that path backwards. And then it jumps forward again, leapfrogs over the top and traces that section backwards, and then leapfrogs. And it does this fascinating leapfrogging behavior that is based on the constraint of the system. And again, this is just an observation we made and what that means in a deep sense and how it's related to giving a model time to think versus not. And is it enough time to think? What happens? What different algorithms does the model learn when you constrain it in this way? I find that quite fascinating and an interesting thing to explore. Does it tell us something about how humans think? Does it tell us something about how we think under constrained settings versus open-ended settings? So there's a number of cool questions you can ask on this front.
You guys are both huge fans of population methods and collective intelligence, and because we can scale this thing up and we can scale it out. And what would it mean to scale this thing out? Not only just in a kind of what do they call it, trivial parallelization, but in terms of having some kind of weight sharing between parallel models and so on. What would that give you potentially?
This is a fun area of research. So one of the active things that we're trying to explore in our team is concepts of memory, long-term memory, and what does this mean for a system like this? So an experiment that one can construct, for instance, is to put some agents in a maze and let them try solve this maze, not how we did it in the paper, but in a very constrained setting where an agent can only see maybe a 5x5 region around it. And we give that agent some mechanism for saving and retrieving memories. And the task, if you wish, is to solve that maze, find your way to the end. And the model needs to learn how to construct memories such that it can get back to a point where it's seen before and know, I did the wrong thing last time and go a different route. And you can then see this with parallel agents in the same maze with a shared memory structure and see what actually happens when you can all access that memory structure and have a shared global, almost like a cultural memory that we can access and solve this global task by having many agents trying to use this memory system. And I do think that memory is going to be a very key element to what we need to do in the future for AI in general.
So the subject of reasoning came up just a second ago, and I think there's a perception that recently we made a lot of progress in reasoning, right? Because it's actually one of the main things that I think people are working on. We released a data set recently called Sudoku Bench, and I was actually quite happy to see it come up organically on your podcast a few weeks ago.
It's more.
Right.
Yes.
So I wanted to tell you a little bit about this benchmark because I think I've been having a little bit of issue promoting it because it doesn't on the surface sound particularly interesting, because Sudoku has a sort of a feeling that it's already been solved. Right? So how interesting can a collection of Sudokus be for reasoning exactly? We're not talking about normal Sudokus. We're talking about variant Sudokus. And what variant Sudokus are usually normal Sudokus, right? So put the numbers 1 to 9 in the row of the column in the box. But then literally any additional rules on top of that. And they're all handcrafted. They all have extremely different constraints. constraints that actually require very strong natural language understanding. So, for example, there's one puzzle in the dataset where it tells you the constraints of the puzzle in natural language, and then says, oh, by the way, one of the numbers in that description is wrong. Right? So you have to be able to meta reason about the rules themselves even before you start solving the puzzle. There are other puzzles where you have a maze overlaid on the Sudoku, and the rat has to work out a way through the maze by following a path to the cheese, but then there are constraints on the path that it takes, so like what numbers and what they can add up to. It's difficult to really describe how varied these variant Sudokus are. And I think they're so varied that if anyone was actually able to beat our benchmark, they would necessarily have to have created an extremely powerful reasoning system. Right now, the best models get around 15%, but they're only the very, very simplest and the very smallest Sudoku puzzles in the set. We're going to be putting out a blog post about GPT-5's performance, and it is a jump, but it's still completely unable to solve puzzles which are, humans can solve. And what I really like about this data set, and actually was the catalyst for me creating it in the first place, there was a quote by Andrej Karpathy saying, okay, so we have all this data, it's from the internet, but what you really want, right, if you wanted AGI, you wouldn't want all of the text that humans have ever created, you would actually want the thought traces in their head as they were creating the text, right? If you could actually learn from that, then you would get something really powerful. And I thought to myself, well, that data must exist somewhere. My first thought was maybe philosophy, like, there's a type of philosophy where you just write down your thoughts without thinking, like just stream of consciousness. I thought maybe that could work. But then when I wasn't thinking about it, and I was, in my leisure time, I was watching a YouTube channel called Cracking the Cryptic,
yes,
where these two British gentlemen will solve these extremely difficult Sudoku puzzles for you. Like sometimes their videos are 4 hours long and they're professionals, like this is their job. And what was perfect, I realized, is they tell you in agonizing detail exactly what reasoning they used to solve those particular puzzles. Right? So we, with their permission, took all of their videos, which represents thousands of hours of very high quality human reasoning, like thought traces, and scraped them and made that available for imitation learning. Right? We did try to do this internally. Turns out that I did a little bit too much of a good job of really creating a very difficult benchmark. Right? So we're still trying to get that stuff working. We publish it that if we have some success. Yeah, I want to really sell the fact that this reasoning benchmark really is different. Right? Not only do you get something that's super grounded, like you know exactly if it's right or wrong, so you can do RL to your heart's content, but you can't generalize very easily. Each puzzle is deliberately designed by hand to have a new and unique twist on the rules called a break-in that you have to understand. And right now, despite all the progress we've made, the current AI models can't take that leap. They can't find these break-ins. Right? They'll fall back to, okay, I'll try 5, I'll try 6, I'll try 7. Right? The reasoning becomes really boring and nothing like what you see in the transcripts that we've open sourced from this YouTube channel. So I just want to put the challenge out there, right? That this is a really difficult benchmark, and I think progress on this benchmark will really mean progress in AI generally.
Could you reflect a bit? So after watching this Cracking the Cryptic YouTube channel, how diverse were the patterns? Because Chris was saying to me, oh, these guys, they go on Discord servers, they get these creative, crazy ideas, and I'm obsessed. Maybe I'm just being idealistic, but I love this idea of there being a deductive closure of knowledge, right? That there's this big tree of reasoning, and we're all in possession of different parts of the tree to different depths. So the smarter and the more knowledgeable you are, the deeper down the tree you go. But in this idealized form, there is one tree, and all knowledge kind of originates or emanates from these abstract principles. And we could, in principle, build reasoning engines that could just reason from first principles, and it might be computationally irreducible. So you have to perform all of the steps, and it feels like because we're not in possession of the full tree, what we need to do is kind of fish around. We fish around to find Lego blocks. Oh, that's a good Lego block. I can apply that to this problem. And maybe that's just what we need to do in AI for the time being. Is we need to just acquire as much of the tree as possible. But could we just do it all the way down?
Yeah, fascinating question. That tree is probably massive, right? And as a human is solving these puzzles, they're definitely learning in real time and discovering new parts of this tree. And it's sort of a meta task, right? Because it's not just reasoning. You're reasoning about the reasoning. And I don't think we have that in AI right now. Because if you watch the videos, they'll say something like, okay, this looks like a parity task, or this is a set theoretic problem, or, maybe I should get my path tool out and trace this around. And of course, the professionals, they do have this already massive collection of reasoning Lego blocks, as you say, in their head. So they'll recognize, okay, that type of rule usually needs this kind of Lego block. It's actually fascinating to watch how good they are at just intuitively knowing, where, someone like me who hasn't solved as many needs to spend a lot of time looking around like, okay, maybe I should try this one, maybe I try this one. But even they're not perfect. So you can watch them take a certain kind of reasoning and start building up, okay, maybe we should solve it like this. And then go, and no, that doesn't disambiguate enough, and then backtrack, and then go down another path. Again, something that we do not see current AIs doing when they're trying to solve this benchmark.
The tree is very big, and I guess the phylogenetic distance between many of these motifs in the tree is just so large, so it's so difficult to jump between. And I think that's why, as a collective intelligence, we work so well together, because we actually find ways to jump to different parts of the tree.
Right, and I think that's probably why the RL, the current state of the RL algorithms that we're trying to apply to this just isn't working. Because in order to learn how to get these breakthroughs, to understand what the sort of nuanced reasoning is to get these puzzles, you have to sample them. And it's such a rare space. It's such a specific kind of reasoning that's required to get to the specific breakthrough, that this kind of technique doesn't work, right? So there's definitely a feeling in the community like, okay, this is how you just solve things now. Like, we have RL, yes, we can get these language models to do what we want. It doesn't work for this data set.
Guys, it's been an absolute honor having you on the show. Just before we go, are you hiring? Because we've got a great audience of ML engineers and scientists, and I think working for Sakana would be the dream job.
That's very kind of you. Yes, we are definitely hiring. And as I said earlier in this interview, I honestly want to give people as much research freedom as possible. I'm willing to make that bet, right? I think things that are very interesting will come out of this. And I think we've already seen plenty of interesting things coming out of this. So if you want to work on what you think is interesting and important, come to Japan.
And Japan just happens to be the most civilized culture in the world.
Right.
It might be the opportunity of a lifetime, folks. So yeah, get in touch. Guys, seriously, thank you so much. It's been an honor having you both on the show.
Thank you very much.
Thank you so much. It's been great.
So when I say deep learning is not so mysterious or different, I'm not saying that deep learning is not mysterious or not different. I think it's actually both. It's rather that the ways in which people often think it's mysterious can be relatively well understood, both intuitively through a notion of soft inductive biases, but also formally in terms of rigorous generalization frameworks that have actually existed for many decades. And a lot of these phenomena can also be reproduced using other model classes. I think deep learning really is distinguished in its relative universality, how broadly applicable it is relative to other model classes. That doesn't mean that it's anywhere close to being completely universal, but it's sort of a movement in the direction of universality, a significant movement. It also does representation learning incredibly effectively. It has properties of its optimization objective, its loss landscape, which are relatively different and surprising, like mode connectivity. And so I think deep learning is certainly different and mysterious, but often not in the ways that people might believe. So I'm very excited to be talking to you both, even though it can be challenging, knowing that there are so many people watching. But I think there are so many fundamental misconceptions in the way that people understand generalization and model construction and artificial intelligence. It's really important to hear a different perspective around, for example, how it's completely fine to build a huge model that will also have a stronger bias for simple solutions, have more of an Occam's razor-like behavior than even smaller models. And these sorts of perspectives actually help us understand phenomena that are often seen as very mysterious, like double descent and benign overfitting and overparameterization, and give us a principled approach for thinking about how we're going to build our own models for whatever properties we're interested in.
There's this fundamental trade-off between bias and variance, and it feels like you're saying you can have your cake and eat it, and you can keep them in the mixture, and you still win. And that just goes against most people's intuition.
So I think the bias-variance trade-off is an incredible misnomer. There doesn't actually have to be a trade-off.
Folks, that interview with Andrew was absolutely amazing. Keith came over to the UK, and we did it in my home studio together a few weeks ago. It's been on Patreon for a little while, and I updated so much based on that interview. Andrew was absolutely brilliant, so I know you're going to love it. But before we kick off, you've probably heard that human data is kind of the dirty secret of Silicon Valley. You know, human data is the reason why these AI models work so well, because the OpenAIs and the Anthropics, what they do is they hire humans to do things like data saturation and evaluation and post-training, and there is a ridiculous kind of uplift from using this human data. Our sponsor, Prolific, what they want to do is produce the first survey on how human data is being used in AI, and if you volunteer and fill out this form for them, they will give you first access to see how you compare. So I'd really appreciate it if you did that. There's no personally identifiable information. Link is in the description. And we are also sponsored by 2 for AI Labs. They are an incredible research lab based in Zurich. They just upgraded their office. They've got an amazing new office. They've hired 13 research engineers in the last year, published in Culture. So he's going through the housekeeper. Go to 2 for Lab, sponsored by conventional wisdom held beliefs.
We should always be anyone's beliefs. You try to understand what do a lot of people believe that might be wrong, and then just unpack that. And it's also very exciting and fun, but it's challenging because, of course, the initial instinct will be to resist whatever you're saying. But then over time, and if you try hard enough, and if you talk to amazing communicators like you two, then you can start to have an influence. And I think that's really important because so much progress has been stalled, I think, by just getting stuck on misconceptions. Like once a certain number of people believe something, it's very, very hard to change their minds, no matter what you say. And I think as a consequence, we've been in all sorts of local minima in machine learning and AI research because we haven't been able to get unstuck from these erroneous beliefs. And there's a whole roster of things like this, like the role of implicit biases, of stochastic optimization and generalization, I think is significant, but also significantly overstated. How we can have really large models that also generalize well, even when there's a small number of data points, is something that is not very well recognized. And in fact, I think is one of the primary drivers of scale being important for achieving good generalization. So not just flexibility, the simplicity bias that comes about through scale. I think another misconception is this idea that
we should change our model depending on how many data points we happen to have available. And this might even be the most controversial one. The reason I don't think we should is because we should always honestly represent our beliefs, and our beliefs about the process that generated our data typically shouldn't change depending on how many data points we happen to have access to. And you can actually demonstrate that these principles work in practice. So you can have models that will be very good when you have a small number of data points, and also very good when you have a very large number of data points. And so this relates to not necessarily needing to have hard constraints, but instead combining expressiveness with Occam's razor.
Yeah, you're only slowly starting to convince me to give up this 10,000 degree polynomial is bad, and I'm only starting to change because you value simplicity, bias towards simplicity as much as I do. And the real key for me was understanding that somehow scale has a bias towards simplicity. And I don't know why or where it comes from, but I believe it, and it's weird.
And can we just set this up? So in your talk last year, your first slide, so you had a bunch of students in the room, and you showed like a fairly sort of simple linear correlated, data.
Airline passenger data.
Airline passenger data. Okay, it was pretty linearly
Some
correlated.
seasonality.
And you said here's three models. One is basically y equals mx plus c or something like that, just a straight line. And I think was the second one something like 10 parameters and 10,000 parameters was the third one. And almost everyone in the room said they preferred one or two. And you said at the end of this conversation, I'm going to convince you to prefer three, which was 10,000 parameters.
And I took a poll at the end, and it did shift, and so that was promising. Yeah, I sort of joke sometimes that if I hadn't met the airline passenger data set, I don't know really what my life would be like now, because it's driven so much of my research. And it's just amazing how people are biased towards choosing the linear function or the cubic polynomial, even if in practice they're not making that choice. Like on CFAR, for example, it's not uncommon to use a neural net with tens of millions of parameters to fit a training set with tens of thousands of data points. And even before deep learning was popular, we were doing non-parametric statistics, where we were working with models like Gaussian processes that were inspired by taking infinite limits of neural nets that are more flexible than any neural net you can fit in memory. And other popular covariance functions as well, like the RBF kernel, really are like saying, I want to use an infinite order polynomial. And so even in these kind of classical statistical models, we're implicitly saying, well, if we're unhappy about the third choice, it's actually because it doesn't have enough parameters. We want infinitely many parameters, not just 10,000 parameters. And I think another way to say this is that parameter counting is a very bad proxy for model complexity. Right. Really what we care about is the properties of this sort of induced distribution over functions, rather than just how many parameters the model happens to have. And so you can have a distribution over functions, which is very flexible. It can represent many different solutions to a given problem, but it can also have very strong preferences for certain types of solutions over others. And strong preferences doesn't mean saying that certain things are impossible necessarily. They can just have epsilon probability. And I think that is really meaningfully different than saying, okay, we're going to have a hard constraint and we're not going to represent those solutions. A, because it's not an honest representation of our beliefs to have those hard constraints, and B, because we see in practice that when we do have these expressive models with simplicity biases, they're much more adaptive. They're much more automatic. So when you have a small data set, it sort of does the right thing. When you have a large data set, it also does the right thing. And so you don't need as much human intervention. And arguably, that's the definition of what really machine learning is trying to achieve. It's trying to build an intelligent system that doesn't require manual intervention. And so I think this is an important principle towards that goal.
You have a paper kind of removing some of the mysteries of deep learning, but I think it's still fair to say it's a bit mysterious where the simplicity bias comes from at scale, isn't it?
It is. So there's some hand-wavy intuition around lost landscapes, and I think this is borne out empirically. So we can sort of understand, for example, that the solutions that we're finding when we're building larger models are more compressible and are flatter, etc. But this is really ongoing research, and I think this is one of the most important questions to understand right now is like, why does scale, rigorously speaking, produce a simplicity bias, and can we get that bias in a more elegant way than just building bigger models?
I was going to ask you why you were a theory, because I know you're a theory guy. Are you a theory guy or an engineer? Presumably you're both, but deep in your bones, are you an engineer or are you a scientist?
It's really hard to choose. In some sense, both. I'm mostly driven by trying to understand things, and so this can be done in a variety of ways. A lot of our papers empirically try to understand model behavior. And so I feel like this is a scientific approach to machine learning. And one thing that really motivates me about this type of approach is whatever you learn will never go obsolete. So quite often, newcomers to the field and even very experienced researchers feel distressed at the rapid pace in the discipline, where you see methods getting published at a conference and then becoming obsolete within a month, or when you go to the conference, everything you're seeing is sort of been replaced by some other algorithm, and wonder, okay, well, is there any point to me sort of investing myself significantly in building a model if I know that it's not going to be used by anyone for any long period of time? And I think one way to address that is really to try to combine what you're doing with an understanding of why things are working. So if you're building a model that gets better performance on some problem, there's a reason for that, and if you can understand the reason for that, that understanding will outlive that specific model and how widely it might be used. And I'm really hoping to do research that will be relevant in hundreds of years from now. And so I think these questions around model selection, for example, in Occam's razor, people will never stop asking. Like, hopefully they'll be able to go back and read not just my work, but like work that's been done in the space and think, okay, this is useful to me, and thinking about how to approach some of these questions. And so in this respect, I would say I'm a scientist, and I try to combine classical theory with empiricism towards understanding model behavior. And I think if you really understand something, hopefully it's something that you can demonstrate in practice. And so I also try to combine some sort of practical demonstration with a lot of the work that I do. And this process also involves engineering. And sometimes understanding those low-level engineering details becomes really fascinating and leads to unexpected intuitions about the principles behind model construction. I think this is something that's perhaps underappreciated. Like quite often, you can have a great idea, and whether it works or not depends very significantly on all the low-level details like numerical stability and other things like that. And when you get really deep into those details, sometimes you can discover things at a higher level that are also very significant in how we should think about model construction and algorithm design.
Cool. So maybe, well, I was just going to share with you, there's a duality that Shannon pointed out that you may like, and it's a duality between past, future knowledge and control. He said, we have no knowledge of the future, but we can control it. We have knowledge of the past, but we cannot control it. And I took that and related it to science and engineering. So the way I look at the two sides of that coin is scientists leverage control to gain knowledge. Engineers leverage knowledge to gain control. So you can be both, because the new knowledge that you collect allows you to better control the environment, the future of the world, and collect even more learning, right?
That's absolutely beautiful. Andrew, we haven't even introduced you yet. Can you tell the audience about yourself?
So I'm Andrew Wilson. I'm a professor at the Krohn Institute of Mathematical Sciences and Center for Data Science at New York University. My work focuses on having a prescription for how to build intelligent systems. What are the key principles involved in model construction? I think although the field has made an extraordinary amount of empirical progress towards building more performant machine learning systems, we're still at early stages of understanding what principles should we broadly embrace when we're approaching our own problems. And so this involves work on understanding inductive biases, so what assumptions we should be making. And so this relates to symmetries like equivariances. Maybe we're modeling molecules or rotation variants, images could be translation variant. How do we represent those invariances? How do we learn them automatically? How do we discover interpretable scientific structure in our data that tells us something maybe surprising that we didn't know before that will go beyond a particular application? then how do we represent uncertainty towards decision making? Arguably, a prediction that's just a point estimate without any kind of error bars associated with it isn't really actionable in the real world. If you have an autonomous car and it says there's a stop sign 5 feet ahead, plus or minus 10,000 feet, you can't really do anything with that information. But if it's plus or minus 1 foot, then you can really act on that information. And observing that almost makes you paranoid. Like, okay, now I really need to represent uncertainty, because if I don't have that uncertainty, then machine learning can't meaningfully engage with the real world. And Bayesian methods, I think, are a really great way of reasoning about uncertainty. And so that also forms a big part of my research program.
Well, welcome to MLST. We have Dr. Duggar in the house. The first time we've met in person we've been doing this for 8 years. 5 years on this channel, but we had the previous channel as well. And Keith came to my wedding on Friday. It's good to have you, man.
Yeah, it's pretty crazy we haven't met until now. It's going to be a blast.
Absolutely. Yeah, we've got some good stuff lined up. I guess just to kick this off, Andrew, I was inspired by geometric deep learning. I interviewed, like Michael Bronstein, Tucker Cohen, Juan Brunner, Petr Veličković. They had this geometric deep learning blueprints. Our video on that did 500,000 views. It was an amazing video. And the basic hypothesis, as Juan outlined, the 3 curses in machine learning, right? So there's the statistical curse, which is that you only have so many data points, and the distance to those data points, or the density of those data points is kind of cursed by the dimensionality of your data. There's the optimization curse, which is that you get stuck in these local minima, and there's the approximation curse. And this is kind of where they're driving to, that you have this function class, and you can be quite opinionated in how you structure that function class. But if you make it too small, you incur approximation error, where the actual test sample is some epsilon distance from the approximation class. And they said that all of these things are cursed. And I guess their prescription was this Platonistic idea that if we constrain the models, so if we add bias to the models with these symmetries, because the generating function of the universe is using these symmetries anyway, then there's no apparent approximation error in doing so. So why wouldn't we do it anyway? I think your ideas are kind of tangentially related to that. You still think we should have biases, but you also think we can have our cake and eat it, so to speak.
So this is a wonderful question, and I've also done a fair amount of work on geometric deep learning, particularly in terms of how we should represent equivariant symmetries in scientific domains. And I agree that it's very appealing to say, well, if we know that some constraint applies to our problem, then we should encode it in our model. And I don't think that's particularly controversial. There are some perhaps surprising results that in some instances, even when you know what the constraint is, you can do as well or better when you don't represent that constraint. And this can be due to the dynamics of how you train your model, etc. But generally, the way I would respond to this is really to say 2 things. The first is there aren't that many instances in practice where we know exactly what constraints we want to have, even when it comes to things like physical conservation laws. So rarely are we modeling, for instance, closed systems. You can have a dynamical system, and maybe you have like a pendulum with like wind in the air or whatever, and now you have some sort of violation of conservation or of energy. And so you want to perhaps instead build models that are just biased towards these constraints without being exactly constrained. Secondly, when you do this, when you represent so-called approximate constraints or you have soft constraints, so you have a model which is very flexible, but it says, well, if we can fit the data in a particular way, then we want to do that. Quite often, it will just collapse down onto those constraints if it provides a consistent explanation of what we observe. And so if you're paying any kind of penalty for deviating from those constraints and you can perfectly explain your data with those constraints, you'll just collapse down onto that. And so I think as a prescription for model construction, it's often going to be fruitful to try to embrace expressiveness, but at the same time, have a simplicity bias, which can be formalized in terms of compression. And this is really an honest representation of our beliefs in many cases. Like another way to describe my philosophy for model construction is just honestly represent your beliefs. And we believe the real world is a complicated place. And if we combine that belief with the idea that simple solutions that are consistent with our observations are more likely to be true, then we can often see desirable behavior in quite a variety of different settings. And so in terms of like having cake and eating it too, I think one of the most surprising findings that we and others have had is that quite often you can increase model expressiveness while simultaneously increasing its biases. So larger models are often more inclined towards simple solutions. And there sort of demonstrations of this that have been just hiding in plain sight, like double descent, this idea that as you increase model flexibility, your generalization error first gets lower, so it improves. As you capture more structure in the data, it gets worse as you start to overfit, and then it gets better again. And in that second descent, typically all of the different models that you're considering are fitting the training data perfectly. So the only possible way that larger models could be generalizing better is because they have some other sort of bias, like a simplicity bias, rather than being more expressive. And so I think time and again, researchers express surprise at the fact that they can have these massive models, billion parameter plus models trained on relatively small data sets that aren't overfitting. But in fact, actually, if they made the models even bigger, they would be less likely to overfit. And so quite often, expressiveness and soft constraints can be aligned.
So if parameters don't solve your problem, you're not using enough of them.
We always want more.
Prediction with expert advice, we know theoretically and for me empirically that by keeping all of these other experts around in the mixture, you pay a cost for that. So in my particular case, having the historical experts in the mixture, every single prediction, they still had some weight. You have to give them some epsilon weight, otherwise they would die. And that actually harms your performance. So the question is it better for you when the new regime comes to pay the cost of learning the regime versus the switching cost of bringing the old regime back? And that's kind of the same with any ensemble or any set of restrictions on biases, really. That there's this fundamental trade-off between bias and variance. And it feels like you're saying you can have your cake and eat it, and you can keep them in the mixture, and you still win. And that just goes against most people's intuition.
So I think the bias variance trade-off is an incredible misnomer. There doesn't actually have to be a trade-off. So the idea, I guess, behind the classical bias variance trade-off is that your generalization error can be compartmentalized in these 2 terms. So bias, sort of how well you are fitting the data, essentially, and variance, like how your fits vary depending on like if you sample different points from this distribution that you're trying to model. And it's true that sometimes if you naively build like a really large polynomial, for example, you can have low bias and high variance, whereas if you build a small polynomial, maybe you have low variance and high bias. However, approaches like ensembling are actually a good way of getting low bias and low variance. And it turns out actually building large neural nets are another way of getting both low bias and low variance. You actually have flexibility combined with a simplicity bias. And this is what's leading to good generalization. And it's sort of another perspective on double descent.
I think here's the way I'll put the question is, and I ran into this as a practitioner, back in the day. So maybe I was just stuck in the hump of having like too many but not enough parameters, to get to the double descent phase. I'm not sure, but I mean, what I experience is that, having parameters in a model, even if they're very, very small, because some, I put in some term in the objective function that forced them to be small, is not the same thing as actually the simpler model that just didn't have them at all, right? Like, I mean, like we kind of, we'll talk about marginalization and kind of Bayesian perspective on that. So like overfitting can be a real problem. So for example, you brought up, conservation. It's like, well, if I'm doing a model and I don't enforce conservation of energy, And as a result, I end up with some small parameters that cause like a little bit of feedback and increasing, energy every single time a robot, takes some action that can cause it to like spin out of control, right? Where I actually did need it to conserve energy and not have that positive feedback. So I guess maybe we're still struggling with, overfitting can be a problem. It's a real problem. It's a known problem. How do we know if we're overfitting in a bad way? Or we maybe don't have enough parameters. We're stuck in kind of the area before we got to double descent, or like how do you in practice avoid the actual consequences of bad overfitting?
Right. So overfitting is real, absolutely. But the conventional wisdom about how we should approach it, I think, is fundamentally misguided. So, and this is rooted in things like the bias variance trade-off. Like, let's constrain our hypothesis space so that we can't have a bad fit to the data that will make bad predictions and so on. Whereas instead, I think if we just embrace the honest belief that there are many possible solutions, even if they're not probable for any given problem, combined with this sort of simplicity bias, we won't tend to overfit. And interestingly, the prescription is almost the opposite of what people think it perhaps should be in principle. Like, build a smaller model is usually the prescription for avoiding overfitting.
Or to enforce simplicity.
Exactly, yeah. Whereas, in fact, as we build bigger models, we often actually start to alleviate overfitting. And double descent is just a great example of this, because that first ascent is from overfitting the data, but then it gets alleviated as we start to make our models bigger and bigger.
By some phenomenon that we still don't really fully understand, like this ability of simplicity to start to come back into the picture as you just make it even bigger.
Right. So in that second descent, the models are typically fitting the training data perfectly, and so the loss is not really the decisive factor anymore between which models we're selecting. It's something else, and so those other biases start to dominate. And so this is actually really important, I think, when people talk about phenomena like flatness. So flatness is this idea that if you perturb your parameters, that you can still get a relatively low value of the loss. And there are all sorts of debates about like the role of flatness and how relevant it ought to be in understanding generalization, etc. But I think what a lot of these discussions miss is it's just one of many properties that control generalization. So if I had to choose between a model that has very high loss but is very flat versus like a very flat solution versus a model that finds a solution that's low loss, that's relatively sharp, I would almost certainly choose the low loss solution. And so when you're in that kind of second descent regime, you now are controlling for the value of the loss, and it's just the flatness of the solutions that's increasing. And so that's sort of one way of knowing maybe like what side of the curve that you're on and thinking about how big should you make your model. But I would also just say make your model always as big as possible. Just try to combine what you're doing with some sort of simplicity or compression bias. And there's a question of like how you do that, but I think there are good ways that we have of thinking about how to do that.
Trick question: is predictive power the same as understanding?
I agree with the idea that representation matters. Representation meanings are how you're solving the problem, even if you're getting the same performance in a particular application. But the reason it matters is because different representations that are achieving the same performance might give you different performance than on different problems. And so if we're trying to build more general agents, we want to understand what sorts of representations are going to provide a better general description of the real world. And so that means we want to avoid things like shortcut learning and so on if it's just going to lead to good predictions in some contrived problem and not really in the real world. And so there's this question of like, can we understand what sorts of distribution shifts we might typically encounter, and can we build methods that have broadly more robustness to a variety of different types of realistic distribution shifts? And I think this connects to things like no-free lunch sort of thinking. So the no-free lunch theorems say that every model is equally good in expectation over all problem sample uniformly from a distribution over all problems. And there are other no-free lunch theorems that say no single learner can be good on all problems. The issue, I think, with these theorems is not their mathematical validity. What they're saying is correct under the assumptions they're making, but rather that the assumptions they're making are not a good description of the real world. So the real world is a small corner of all possible data sets. It's not drawn uniformly from a distribution of all possible problems. If we were to do that, we would mostly just get noise. And so the question then is, to what extent is the structure across real world problems shared? And at what level of abstraction can we represent that shared structure? And so my contention is that the distribution over real world data is biased towards local number of complexity, and so are some of the models that we started to develop.
Yeah, but can you give an example of where it was hard to confront a misconception, why it mattered, and what the process involved?
There had been this sort of approach where you would take some approximate Bayesian inference procedure and pit it against deep ensembles as the non-Bayesian alternative. Yeah. And normally I actually don't care that much about what's being called Bayesian or not. Like the same with like intelligence, what is whether something's a good representation, all these things. Let's just connect this to whatever problem we're trying to solve. But this was actually kind of problematic because the takeaway seemed to be that if deep ensembles were working better than some Laplace approximation or some MCMC procedure, then the answer is to be non-Bayesian, to be less Bayesian than we have been historically. And that's turned out to be exactly the wrong sort of directionality for how we should think about model construction, because for a given computational budget, those deep ensemble procedures were actually doing a much better job of approximating the posterior Bayesian predictive distribution, so doing marginalization. And so in fact the prescription should have been, well, we actually need to be more Bayesian. And so like this was sort of a frustrating thing, but it was also very difficult to approach because there had been so many papers where people had just written basically that these deep ensembles are the non-Bayesian alternative. And so kind of coming out and saying, well, actually they're doing a better approximation of the Bayesian ideal than all these methods that are being called Bayesian is sort of, confronting, just sort of hundreds of papers in some sense at once. But it felt like a very important thing to do. And we had actually done it subtly in a lot of papers where there'd be some subsection of some paper that mentioned something like this, but that was never really internalized because it was never front and center. So I thought, okay, a blog post is the right way to do this. And let's make it all about this. And I think in the end, actually, it was the blog post that changed people's minds. I never saw a paper after that where people were making this separation. But also I think, it did sort of strike a nerve a little bit.
Yeah, but how should we approach model construction? How can we embrace expressiveness without overfitting?
And so when I say I want to embrace expressiveness, there is some subtlety associated with that idea. And that basically means that in some cases, maybe we're wanting to represent lots of solutions, but we're assigning them almost zero probability, but not zero probability. So they're possible, but not plausible solutions in our view. And then if the data is telling us something that like, well, actually we really should be paying attention to a certain type of structure that maybe would surprise us, the model can actually respond to that. And if that structure isn't actually there, then your model isn't going to perform a lot worse than the model that is exactly constrained in those ways. In terms of how we should approach model construction in general, if you have a soft bias, a gentle encouragement towards certain types of constraints over others, quite often you can do as well as the perfectly constrained models. And the reason is you're paying some sort of penalty, even if it's small, for deviating from that constraint. So if you can fit the data perfectly with the constraint, you'll just collapse down onto that model. And we noticed this in a work we had called residual pathway priors for soft equivariance constraints. And so this was a Bayesian mechanism essentially to have a distribution over solutions which would be concentrated in some way around certain types of equivariance constraints. Just for the sake of the audience, equivariance is a generalization of invariance. It basically means if you have some transformation t, f of tx equals t of f of x, rather than f of tx equals f of x.
Like a CNN, for example, so it commutes in that case with the translation.
Exactly right. So if you translate the image in some way, the pattern of activations will translate in the same way across the different layers, rather than them just staying exactly the same, which would be invariance. So in this paper on residual pathway priors, we were interested in the strength of the soft bias. So we basically had a distribution over neural net parameters that had a covariance matrix that lived in some equivariant subspace of our choice plus some orthogonal complement. And so there'd be these weighting terms basically that would represent how strong do we want this bias to be for equivariance. And surprisingly to us at the time, it didn't matter very much. Like as long as you had a very soft bias for the constraint, it would often be as good as even a perfectly constrained model. Basically for this reason that you're still paying some penalty for deviating from the constraint. And so if it is a good description of the data you fit perfectly, then you often collapse down onto that constraint. Although I wouldn't want to dismiss the importance of trying to calibrate these biases. It can matter in certain instances, but in a lot of instances, a very gentle bias is sufficient.
So maybe just to put this into perhaps more familiar territory for other Bayesians out there, like the assignment of priors just for parameters. It's always the goal to try and find a prior that's relatively ignorant, but encodes some very soft, type of constraint. Like maybe it's a scale invariant parameter or a scale invariant prior or location invariant, kind of prior. And overall, a lot of times these priors are maybe worth like 1 data point or 2 data points, but they're small enough that they can be overridden quite easily by enough data. But even that small amount is enough to avoid sort of stupid answers, like that like the chance of a head is infinity or something like that. Is it kind of analogous to that, or?
I think that's a reasonable analogy. I would also add that we can't get away from making assumptions. So even though I'm in favor of embracing expressiveness and having relatively soft biases for certain types of solutions as opposed to hard constraints, machine learning means learning by example, and we can't do that without making assumptions. The question is just what assumptions should we be making and at what level of abstraction? And perhaps it's enough in a surprisingly large array of different problems to embrace expressiveness in combination with some sort of simplicity, some Occam's razor bias that can be formalized in terms of compression.
Empirically, simple models work better.
Ironically, given the surprise people often express at this idea of wanting to always embrace flexibility, is that like before deep learning, the community had started to come on board with this notion that we want arbitrarily flexible models. In fact, the class of models that I was working on in my PhD, Gaussian processes in machine learning, were kind of inspired by this idea that we want really, really large neural nets. And Radford Neal, a statistician at Toronto at the time, working in Jeff Hinton's group, was saying, okay, we want to build models the size of a house, and I'm a Bayesian, and I'm going to really embrace expressiveness, so I'm going to take an infinite limit of a neural net with an infinite number of hidden units, and this is going to converge actually to a Gaussian process using a central limit theorem, arguing with a particular type of covariance function. People are like, well, that's amazing. Let's just use Gaussian processes because they're so much more principled in a lot of other ways. Like they're less sensitive to a bunch of design decisions, etc. They can be written in a very small number of lines of code, and everyone anywhere in the world is going to get basically the same answer, etc. And so people sort of moved in this direction of just embracing expressiveness. But then once we started working in these kernel formulations, I think people perhaps started to forget that there was this dual space correspondence, and we actually were working with models that were more flexible than any neural net you could fit in memory, and finally we were achieving very good generalization, especially on problems with a relatively small number of data points. So now to get back to your question, Radford Neal also had an interesting quote, I believe, in his PhD thesis, that whenever you have a simple model that performs well, you can always build a more complicated model around it that will perform even better. And he gives this example of handwritten character recognition, where you might have irregular writing styles, weird ink blots on the page, just some sort of structure that you probably haven't already accommodated in your model that you can try to accommodate, and you'll achieve better and better performance. So what I would do in the situation you described is really try to understand what's the inductive bias there that's leading to good performance, and how can I soften it in some way? How can I generalize this in a way that still honestly represents my beliefs?
So, but there seems to be something wrong with this quote that you can always build a more complex model, because maybe you can always build a more complex model that has a higher likelihood on the training data, but overfitting is a real phenomenon. Like nothing in your work says that overfitting doesn't occur and can be harmful. So it's like there have to be situations where if you diverge from the ground truth model, I mean, I'm sure I could just build a system that has a ground truth model, simulate data, and provably show that a more complex inference doesn't generalize as well. So that has to be true. So how do we know in reality when we step too far?
It's a great question. I think we have to be careful about what we mean when we say a complex model. So I think most people would not consider Gaussian processes with an RBF covariance function, which is the standard covariance function kernel that's often used, to be a complex model, but it's highly expressive. So it's more expressive than any neural net we can fit in memory. It just has very, very strong preferences for certain types of solutions over others, and this enables it to be extraordinarily data efficient. So one of the main use cases these days for Gaussian processes is in something called Bayesian optimization, where you're trying to maximize some sort of black box objective. So it's not something you have a closed form expression for, like it could be generalization performance of a neural net as a function of some of its hyperparameters, for instance, or some really costly physical simulation as a function of some parameters, and you basically want to query this objective as few times as possible in order to achieve a good result. Gaussian processes are an amazing surrogate model for this objective, and you use the uncertainty to do the exploration efficiently. So I think that you can have expressive models that aren't necessarily complex. They still have very strong simplicity biases, very strong preferences for certain types of solutions over others, but at the same time, they're representing a wide array of possible solutions to the problem. And I think that's how you can kind of reconcile what Radford Neal was saying with what we see in practice around things like overfitting. So I think there's a common misconception that the expressiveness of a model and its inductive biases are at odds with each other. The more expressive the model, the weaker its assumptions in some sense. Like the fewer inductive biases it has, the less data efficient it will be, etc. And what we found, which has been quite exciting, is that the larger you make, say, big transformers, actually the stronger its inductive biases. Like the models get both more expressive and they have a stronger simplicity bias. And so I think you can expand these two things together in some sense, and this is how you can avoid, say, overfitting and other sorts of issues with not achieving very good generalization. And I think one of the clearest demonstrations of this is in a phenomenon called double descent. So double descent is this phenomenon where typically on the horizontal axis you have the expressiveness of the model, the number of units, for example, in each layer of a residual neural network, and on the vertical axis you have generalization error. And so initially generalization error decreases as you increase the expressiveness of the model, and it's able to fit the data better and capture more structure. And then it starts to decrease, it starts to go up, and that corresponds to some sort of overfitting. And then it decreases again, and that's why it's called second double descent, because of that second descent. And in that second descent, all the models typically have about zero training loss. So the training loss just keeps going down as you increase the expressiveness of the model until roughly the number of parameters equals the number of data points. And what that means is that the larger models in that second descent cannot be generalizing better because they're more flexible. They're all fitting the training data perfectly. It has to be that the larger models have some sort of bias, which is enabling better generalization. It turns out that this is a simplicity bias, a compression bias that we can measure.
Yeah, but let's talk through that a little bit. So, as I understand, your thesis is that there is some kind of generating function of the universe, and in some sense, it's quite simple. Francois Chollet talks about this. He talks about the kaleidoscope effect, that we have the generating function, and then it gets composed together in a myriad of different ways, and we see the kaleidoscope, and intelligent people can decompose the kaleidoscope back into the original generating function. And you've also said that natural data in particular is quite low dimensional, quite simple, and that neural networks prefer simple data. And even I want to take a slight issue with that, because what I find is that neural networks in the early stages of training prefer simple data, and when you continue to train them, they seem to complexify and learn more high frequency data. So how do you think about that?
It's a great question. So it's a really important observation that neural nets tend to learn structure before they learn noise and things like this. There's a question around to what extent being able to fit noise is hurting their generalization capability. So there's this other phenomenon called benign overfitting, where the model fits typically a mixture of signal and noise, but the noise fitting the noise doesn't significantly degrade its generalization performance. And this is often seen as something that's specific to deep learning and in the face of everything that we know about generalization. And that's partly because classical frameworks are trying to understand generalization, like VC dimension and random complexity, are essentially measuring a model's ability to fit noise. However, there are other generalization frameworks like PAC-Bayes and countable hypothesis bounds that we explore, which don't penalize an expressive hypothesis space and instead try to understand what sorts of soft preferences the model has for certain solutions over others. And we've been able to achieve fairly tight bounds on the generalization performance of these large models using something called a Solomonov prior. And so a Solomonov prior says that we actually have a maximally overparameterized model. We can represent every possible program on a computer, that we have exponentially stronger preferences for solutions that have what are called low Kolmogorov complexity. And so they're very compressible. The Kolmogorov complexity is the shortest possible program that can generate our hypothesis. And the fact that we're able to get these tight generalization bounds for these very large models, and in fact that the models get sort of better, that the generalization bounds get better as we make the models larger, suggests that this is not a bad description of how these models are actually behaving. So doing induction with a Solomonov prior is called Solomonov induction. And so it seems that when we make these transformers, for instance, very large, we're combining this expressiveness with this strong preference for low Kolmogorov complexity solutions. Another observation that's been made is that models are becoming increasingly general purpose. And so 20 or 30 years ago, the typical prescription was to encode as much expert knowledge as possible into the model you're constructing and tailor it very specifically to the problem that you're considering, because of results like the no-free-lunch theorems that say that every model is equally good in expectation over all problems sampled uniformly from this distribution over all problems. There are several no-free-lunch theorems. Another one says that a single learner is not going to be good on all problems. Now, these results are mathematically correct, but they don't really correspond to the real-world data-generating distribution. The real world is a small corner of all possible data sets. It's not drawn uniformly from that distribution. If you were to draw data sets from that distribution, you would mostly get noise. And so I guess the question is, well, what is the real-world data-generating distribution really like? And it seems like there is a bias towards generating data with low Kolmogorov complexity, and our models share that bias. And this is why we've seen increasingly general systems. So we've moved from feature engineering, basically hard coding structure into our models, to more modality-specific models and architecture. So convolutional neural nets for vision, recurrent neural nets for sequences, language, etc. MLPs for tabular data and regression, to transformers for almost everything. And so this isn't to say that transformers have achieved general intelligence, absolutely not. But they're, relatively speaking, more general than the predecessors. And we have seen this kind of movement towards increasingly general models. And our contention is that this has been made possible by aligning with the real-world data generating distribution, which seems to have a bias for low Kolmogorov complexity. And we had this paper on no-free-lunch theorems, inductive biases and Kolmogorov complexity. And I think one of the most surprising findings in that paper was that convolutional neural nets, which were clearly designed for image recognition, so they have locality and translation equivariance and so on, provably have inductive biases for tabular data shaped as an image. And the only possible reason that could be the case is because they both sort of share this bias for low Kolmogorov complexity. And that bias gets stronger as we make the model bigger.
Okay, so I have actually two questions about this, and it's about the Kolmogorov complexity. So I think if I heard you correctly, on the one hand, you're saying that just stock neural network training of today, so just transformers, SGD, batch norm, whatever people are doing, seems to empirically exhibit bias towards lower Kolmogorov complexity models, and this shows up by their generalization kind of falling within this bound that you found. And then you also mentioned Kolmogorov induction, which I believe would be explicitly introducing a kind of penalty term or a risk term, an objective part of the objective function that has to do with Kolmogorov complexity and kind of maybe pushing the model a little bit further towards simple. I think you're talking about both. So maybe if you could elaborate, and also where is this bias towards simplicity coming from? Like everybody knows the algorithms. Like which part of the algorithm is inducing this simplicity bias? Is it because we're using floating point numbers, IEEE, or what? Like where's it coming from?
This is largely an open question, although there are some intuitions, and this is something I'm really excited about pursuing further in my research. Where does the simplicity bias, especially from scale, originate? There are some intuitions, so geometric intuitions around the loss landscapes for the objectives that we use to train these models. And so when we're sort of minimizing training loss, we can try to geometrically understand the properties of this landscape that we're minimizing. So it's been observed, for instance, that flat solutions, meaning solutions where you can perturb the parameters by some amount that retain low training loss, tend to generalize better than sharp solutions that have the same value of the loss. And you can make a compressibility argument for why that's the case. Flat solutions don't need to be represented with as much precision, and so they're more compressible. As you grow the size of these neural nets, the relative volume of these flat solutions starts to exponentially dominate the volume of the sharp solutions. And so you can imagine heuristically.
Well, why is that? I mean, do we know why, or it's just an empirical observation?
Yeah, so we know why to some extent, but our understanding is somewhat heuristic. And so you could imagine, for instance, having a region of the loss surface with radius RA that's flat. So you perturb your parameters within that radius and you have a low value of the loss. Another region with RB that's where RB is much less than RA. Now, as you grow the number of parameters in your model D, RA to the D starts to really dominate relative to RB to the D. And we seem to observe this in practice. So there was a result, not from my group, from Tom Goldstein's group at the University of Maryland, where they were trying to understand the role of the implicit biases of SGD and stochastic optimization in generalization. And so quite often, as you perhaps have alluded to, SGD is often thought to be a really integral component of achieving generalization in deep learning. There's this idea that we have these very complicated objectives that we're minimizing that are very non-convex, etc. And SGD somehow saves us, that the implicit biases of SGD navigate our procedure through some region of the loss landscape that represents low-loss solutions that do generalize rather than low-loss solutions that don't generalize well. Well, it turns out you can actually do full batch gradient descent and achieve pretty comparable generalization to what you would get if you're using SGD, even if you don't try to make that implicit regularization explicit in the loss. And there was another paper that showed that if you even do guess and check, so you just randomly sample your solution vector and then stop when your loss is below a certain threshold, the generalization will also be fairly comparable to what you get if you use SGD or Atom. And so that corresponds to this geometric intuition. If you're just sort of throwing darts at the loss landscape and then you stop as soon as you have loss below a certain threshold, you're much more likely to be in this region of low loss and good generalization than low loss and bad generalization as you increase the number of parameters in the model. Now, this is not an airtight argument, so there are lots of ways that you can increase parameters in models and not really influence the geometric properties of the loss landscape. However, it does seem to correspond to what we observe empirically, and not just in terms of results like guess and check. If we look at something like double descent, in that second descent, we can measure something called the effective dimensionality of these models. So that's the number of relatively large eigenvalues of the Hessian, which is sort of the number of sharp directions essentially in the loss landscape. And so that decreases as we make the model bigger.
So interesting. Into the second question about explicitly introducing penalty term for Kolmogorov complexity. Have you done much of that? Looked into that? Is that useful or just not necessary?
It's something I've been thinking about. It's very hard to operationalize. So you can evaluate these bounds by computing an upper bound on Kolmogorov complexity, measuring the compressed file size of your model after training. But in order to use that prior as some sort of regularizer, you would need to be considering sort of compression of some whole set of different hypotheses, not just a single hypothesis that's found by the model. And so there's an open question of how you could try to operationalize that. Like Solomonov induction is sort of represents an idealized learning system. It's not something we can really do exactly in practice. It seems that neural nets are sort of approximating it, and that's evidenced by these bounds and how they're able to tightly characterize generalization behavior of these models. But it's hard to sort of turn into some kind of regularizer. I'm also interested in how we can go beyond things like Kolmogorov complexity. So Kolmogorov complexity doesn't distinguish between incompressibility due to randomness, so like noise, for example, in our data, versus structural complexity. And Scott Aronson actually had a really interesting blog post related to this about 10 or so years ago, where he was imagining a system, he had this kind of physics analogy, where you have coffee and cream, and initially they're separated liquids, and you start to stir them together. And as you do this, the entropy of the system is increasing.
I've seen that one. That was shared on our Discord recently.
Yeah, very nice. Okay.
Join our Discord.
I'd love to, yeah. We actually have a, don't get ahead of myself. We have an idea, of course, for how we can do this. But so the blog post sort of compares this to, so the entropy of the system is increasing, the Kolmogorov complexity is increasing. But the intuitive sophistication of that system is kind of non-monotonic. Initially, it has low entropy, low sophistication, then sort of intermediate sophistication and entropy, and then again, sort of like, and then high entropy and kind of low sophistication. And so you can think of this in a machine learning context in terms of reasoning about the value of data. So if I sample data from like a random uniform distribution, that's going to be very incompressible. I'm going to need to memorize it. It's sort of uncorrelated. It's going to be useless for learning a representation, for training my model. I could alternatively imagine some sort of sophisticated cellular automata problem, some sort of game-of-life problem with very sophisticated generalization rules. That data actually could have an extraordinary amount of value for learning a representation. There was a paper that looked at something briefly like this called Intelligence at the Edge of Chaos, and I think there are other results like that are coming out that like you actually might want to train your models on this data with a lot of structural complexity, even if you really want, in the end, the model has some kind of Occam's razor bias, etc. And so we've been thinking about kind of measures of information that might compartmentalize structural complexity and random complexity, and this will help us reason better about the value of data and developing priors sort of that are like Solomonov priors, but might actually be more directly addressing the type of incompressibility that we're interested in.
Yeah, I mean, so you said so many interesting things. I mean, first of all, to Keith's point, you were saying that this isn't a penalty term, yet your hypothesis is that neural networks implicitly do this kind of compression, which might be correlated or related to this Kolmogorov complexity. So many folks just kind of, they equate intelligence with compression. And when I spoke with David Krakauer, he took umbrage with that. He said, compression is a component of intelligence, but there are so many other things going on as well. And certainly when we look at things like the ARC challenge, there are so many possible solutions. So a naive heuristic of just selecting the simplest program isn't always the best thing to do. There are many possible selections that you could make. And, so you demonstrated this upper bound, which used this complexity term. And in a sense, that's saying that it could be no worse than this, rather than it could be, but it could actually be so much better. And our empirical experience of deep learning models is that they seem, we call it shortcut learning basically. They seem to have found some superficial generalizing thing which does all the things you said when you mentioned the no free lunch theorem. So you could take a CNN and you could use it on tabular data, you could take a transformer and you could use it on audio data. So it's almost like what we've seen is that we've hit this, for want of a better word, local minimum. And it feels like we need something more to get to the real understanding of some of these problems. Does that make sense?
So is compression intelligence? I think this is a big debate right now. I think it is very closely associated with intelligence in a lot of ways. If we can compress our data really effectively, then in order to do that, we're discovering regularities that are typically going to help enable generalization. And in some sense, physical laws, for example, are a great compressed representation of reality. And so I think that compression is really intricately connected with what we mean when we talk about building intelligent systems. There are instances in which this can go very wrong, like in shortcut learning, where, for instance, you might have some spurious correlation, like maybe every time there's a blue pixel in an image, the label is a bird or something like this. And so the model, forgets about the foreground and it just looks for some feature in the background. In terms of generalizing on that distribution, that's actually not a bad idea. That actually is the right thing to do. So Occam's razor is really a good principle. But if we go out of distribution, so we see like a bird in, with a volcano or something behind it or in a room, then, it's not going to arrive at the right label. So there's this question of like, are there other principles of induction that will lead to greater robustness under distribution shifts? I think in general, Occam's razor still is the right thing to do. Like there are many cases where a compression will actually not give you what you want more broadly if you move beyond that distribution. But in an absence of additional information, it seems like you can't really do better as a guess as to what's the right strategy. And so I still think Occam's razor is a very robust principle of induction. And perhaps one answer is just more data. I think this will work well in some cases and not in others. So we have some work in progress on trying to build transformers for matrix operations. So this is actually kind of analogous to the work that people have done on transformers for multiplication, addition, things like this. So I guess, these systems, LLMs, seem very impressively effective in some instances in being able to write and code and solve a variety of different problems we didn't really expect them to be able to solve. In other instances, they're just shockingly bad. So how many R's are in Strawberry, like all reversing strings, counting, and just basic addition and multiplication, etc. And so there's this debate, I think, about whether we should be giving them tools to do those things. Like why not just give them a calculator? I mean, whatever they learn to do in terms of adding and multiplying numbers is still not going to be as efficient as giving them access to a calculator. So why don't we just do that? Or like, is there some sort of greater value in having to sort of learn a representation that can do some of these things? Because maybe even though we always want to use a calculator, if we're multiplying or adding numbers, being able to do something like that reasonably well might transfer into other settings that we don't really anticipate. And I'm probably more in this category. Like I just think intellectually we should try to figure out how to do this without tools. And so this work that we're doing on transformers or matrix operations, I think is quite analogous. So you could argue that addition and multiplication are just fundamental primitives for trying to build intelligent systems. We're not as good at it as a calculator is, but it might be important for us to have some ability of being able to do these things. The same could be said of matrix operations. This is really the backbone of all sorts of different learning algorithms, like Gaussian processes, which we discussed a little, involve solving linear systems with the covariance matrix, computing log determinants, etc. Degenerative models like normalizing flows involve log determinants, dimensionality reduction like PCA, etc. involve other matrix operations. And so they're just really ubiquitous as kind of a primitive for trying to build learning algorithms and intelligent systems. And so I think if transformers are ultimately going to become some sort of general intelligence, then they ought to be able to be competent at these types of operations. And so we were kind of representing then matrices as sequences of numbers and then having the outputs be things like the maximum eigenvalue or solution to a linear system or whatever other operation we were considering, the spectrum of eigenvalues. And we found interestingly that when you train this approach on Gaussian random matrices, you just sample every entry of the matrix from a standard normal distribution, it will do fairly well at in-distribution matrix operations. So other matrices sampled from that distribution it hasn't seen before, but extraordinarily poorly, even if you go slightly outside of that distribution. So given an identity matrix, all ones in the diagonal, zero everywhere else, that'll have pretty low density, has support under this Gaussian distribution of matrices, but pretty low density under it, hasn't seen something very much like that. It will just completely fail. It won't do anything reasonable. And so we considered a number of interventions like looping, sort of adaptive pastime computation, enriching the training distribution very significantly. So having sort of this like Einsam
space of structured matrices that we were sampling from. So all sorts of different matrix structures, Topliss, Kronecker, etc., block diagonal, low rank, and a variety of other interventions. And interestingly, we found once we had done that, this approach actually was able to generalize even to matrices that were out of distribution for this fairly rich sort of training set that we created. And so it seemed to move more towards learning an algorithm rather than just doing statistical interpolation on the training data. And so this is, I'm an optimist by nature, so I am very happy about the fact that we can use data to move towards things like algorithm discovery. But now I remember why I started talking about this. So I think there are instances where it's going to be hard. So autonomous driving is an example where like you have outliers, but they're different each time. So just training on the outliers isn't useful because there are going to be new outliers that look very different from those outliers. And I just have the intuition that more data alone is not really the answer to building robust autonomous driving systems.
Yeah, I just want to say, as far as why not just give them tools? I mean, my answer, folks, is because those have to be programmed and built by people. And the whole point here is to allow machines to do their own programming, right? Machine learning. And if they can't even learn to do multiplication reliably and to generalize from decimal multiplication of binary or hexadecimal in 9 digits to 36 digits, what hope do we have that they're going to discover relativity or non-Newtonian mechanics or any other kind of frontier things, right? I mean, isn't that part of the goal here?
Absolutely. And I think being able to do certain things well, we're finding might surprisingly relate to doing other things very well. And so I think we have seen this to a large extent with LLM. So we had a paper where we just took a text pre-trained LLM off the shelf and applied it to time series forecasting. So we did everything naively. We weren't even really intending for this to be like a proper project or a paper. We were just curious, if you just give GPT like a sequence of numbers naively encoded to strings and have it extrapolate the next sequence of string tokens, how would it compare to purpose-built time series forecasting procedures? And it just worked way, way better than we thought it could possibly work. It didn't even really make sense. And so we did sort of turn this into a proper project. We did a little bit of work on trying to improve the tokenization and think about uncertainty representation, et cetera. But most of that paper, it's called Large Language Models or Zero-Shot Time Series Forecasters, was focused on trying to understand how this is even possible. And in the end, it did start to feel a bit more like maybe it's not just that you can do this, maybe you should do it in some instances. Like they did quite well on a variety of benchmarks. And to me, this suggests with like a proper dedicated research effort on LLMs for time series, we could see these systems actually working a lot better than the purpose-built models. And so what that shows is being able to predict the next words in sentences can actually transfer to being able to do other things like time series prediction really well. And we had another paper on LLMs for materials generation, which was kind of similar. So we took a text pre-trained LLM off the shelf, like a Llama 2 model at the time, and we fine-tuned it in this case on atomistic data represented as text, so locations of atoms and energies and things like this. And the resulting system was able to generate inorganic crystals with favorable properties better than these purpose-built approaches and even foundation model approaches that had been trained on that domain-specific data. And so one of the takeaways from that project was like the text-based pre-training was an indispensable component in being able to achieve good results on materials generation. And we tried to understand also in that paper why that was the case. We were collaborating with some chemists at FAIR in California, and they were just very curious about LLMs and foundation models, so they were willing to sort of humor us a bit and help us sort of see what we could do. But they were just like skeptical throughout the project until we saw the results. And it's like, well, you can't deny the results are great. Why is this happening? And part of it was that in being able to predict the next tokens in strings, you are learning principles of induction like Occam's razor. And so how do those sort of manifest themselves in context learning? So what it means is and in fine-tuning. So what it means is these models are going to be predisposed to discovering compressible representations. And that means, for example, salient symmetry. So this was a problem where there was a rotation invariance. And these models actually were very quick to learn these kinds of invariances because of the text-based pre-training. It sort of instilled this principle. And so I think this is also an example of how compression can be a broadly applicable principle for induction. It's at the right level of abstraction that you can start to see more relatively universal behavior. So for instance, there are some theories on the success of foundation models that suggest that different problems are just different projections of some underlying reality. So like Platonic representation hypothesis is an example of this. And so you can represent an image with pixels or with words and train the respective models on those different modalities and learn similar representations. I think that can be true in some instances, but I also think different problems are often truly quite different from each other in terms of their low-level structure. So like if we have molecules, there's rotation invariance, maybe some other problems, some image recognition problem, like character recognition, we might have translation invariance. Doesn't matter if the 2 is on the left of the screen or the right of the screen, the label is still a 2. These are very different low-level feature representations. So like the architectures that you would typically use for each of those modalities and to respect those different types of invariances would look very different. But what they have in common with each other is they're both ways to compress the respective problems that they're being applied to. So if you have a model that has this compression bias, then it can discover those salient symmetries. And we had this really surprising finding that vision transformers actually can be more translation equivariant than convolutional neural nets after training, which sounds impossible because conv nets by design are translation equivariant, but they're not exactly translation equivariant because of aliasing artifacts and edge effects and things like this. And so this other model, this transformer with no explicit constraint whatsoever, just a soft bias that manifests itself increasingly at scale, is able to discover a solution that has lower equivariance error than the convolutional neural net, which is just absolutely remarkable. So to come kind of full circle to your question, I think that we're discovering more and more that being able to solve certain problems really well will translate in perhaps unexpected ways to being able to solve other problems well. And so I think especially when it comes to things like addition and multiplication and matrix operations, these are just even like obviously like fundamental primitives for building intelligent systems. Like even if we can use tools for those things, we want our representations to be somewhat competent at them because it's going to be useful for all sorts of other things we probably haven't anticipated.
So Occam's razor has been mentioned multiple times in the last few segments. I want to dive into that because I love Occam's razor, and I first came to really understand it when I became a Bayesian, and it's nice to have a fellow arch Bayesian and to talk with here because in Bayesian inference, if you will, Occam's razor has a very explicit form, like mathematical form, and it's marginalization, right? It's saying like if you have all these parameters around and you compute the average, you do this integration over all these parameters, that really that's telling you like the probability of the model, like given your full parameter space having been integrated away, and that's really where you get let's say a penalty for complexity comes into play with marginalization. It's like if you expand your model's flexibility or you make it more complicated without any gain in inference, well then that kind of like counts against you, or without any gains of some weird simplicity in the form of less curvature, things like that. And I was looking at some of your talks, which were really great from 5 years ago. These Bayesian tutorials, Bayesian deep learning tutorials you had, I think when you first went to NYU, I really enjoyed them. And there was a lot of talk about marginalization and the importance of it and the intuitions that you gain from that. And I think, but more recently, that's played less of a role in the conversation, or people have just given up on trying to do the integrals and they're just back to doing maximum likelihood and maybe with some hacks in the objective function. So I'm just kind of curious, as a Bayesian, your journey going from understanding like the beauty of marginalization and Occam's razor built into Bayesian inference versus what you do as a practitioner, what you see people doing in practice, how it's playing out in the field or not, and maybe is there a future in which marginalization and doing these computational intractable integrals or something could play a role in driving like even better, machine learning and inference?
I'm so glad you asked. So there's almost nothing I like more than talking about Bayesian inference, and I'm so glad you said marginalization because I feel like that's often overlooked. Like when someone says Bayesian, probably the word that comes into most people's mind mind is prior, and is the prior good, and how do we know what would a good prior be, etc. And they get worried about that. But really, the prior is not the defining feature of what it means to be Bayesian. Instead, being Bayesian means that you want to represent the honest belief that you have uncertainty over what solution is correct given a finite data sample. And so if I'm trying to estimate, the bias of a coin that I'm flipping, if I flip it once or twice, regardless of whether it comes up, heads twice or something like this, I ought to have some uncertainty over the bias still. And that uncertainty is manifested through this procedure called marginalization. So I think we can think of regression to get some intuition of this. So we could imagine like a bunch of different points on a sort of y-axis plot, and maybe the points look roughly like they're on a straight line, but not quite. We could also imagine that there are many different curves that will perfectly run through all of those points. All different from each other. Some of them will be very wiggly, some of them will be slowly moving, etc. Some of them will basically just be like a straight line. And we wouldn't be able to say, well, we know with 100% certainty it's this curve. That's the right description of our problem. But that's exactly what we're doing, 100 minus epsilon % of the time when we're training models in deep learning. That is not an honest representation of our beliefs. And it's going to become a bigger and bigger problem the more expressive our model actually is. Because that means there are going to be many more different settings of parameters that are consistent with what we observe. And we're just betting everything on one of them. And probability theory says, no, that's just wrong. That's not what you should be doing. The sum of product rules of probability say you should be doing marginalization. And so that's all to say that Bayesian marginalization, basically looking at all possible solutions that can be expressed by your model class, weighted by their posterior probabilities, is going to be most important when we have a model that's very expressive, has a lot of parameters, so deep learning, for example, especially relative to the number of data points that we're considering. And I think often people think of it in the opposite way, that like, oh, maybe Bayesian methods are most relevant in the realm of classical statistics, like if you're doing some logistic regression and maybe you want to represent some uncertainty, etc. But it's not really suited for deep learning. It's really the opposite. The challenge then is how do we do this in a way that's computationally tractable? And I think like with most things in life, the answer of course is nuance. So it's not that like we can either be fully Bayesian or not Bayesian at all. Let's just try to do what makes sense given the resources available to us. And so like if we're just doing standard training, you can actually view that as a very crude form of marginalization where you're saying, okay, I'm representing the posterior as a point mass around the most likely setting of parameters. And then we can say, okay, well, maybe the posterior, which is really like so the loss functions that we're minimizing are basically negative log posteriors. Maybe the posterior looks nothing like a point mass, it looks nothing like a Gaussian, it's very multimodal, it's very messy, but we can still do a better job of representing it with a Gaussian than with a point mass. And so let's use a Gaussian approximation. And indeed, when we do that, we often see better generalization because we're representing all these other complementary and compelling explanations to our problem. And then we can keep taking it from there. Okay, maybe we can develop some MCMC procedure that will explore the loss landscape and capture something much richer than just unimodal Gaussian structure, etc. And again, we see improvements in performance in doing that. And so I actually think that Bayesian methods have been an extraordinary success story in deep learning and beyond. But we don't hear as much about them now as we did maybe 10 years ago. And I think there are a number of reasons for that. So to some extent, they're a victim of their own success. So I think there was some low-hanging fruit in being able to do better approximate marginalization in neural nets around 2015. And there was really a lot of progress between about 2015 and 2020 in achieving increasingly better results that will also be kind of computationally efficient. So there are procedures like one we developed called SWAG, for instance, which was based on some insights we had into the structure of these loss landscapes that will allow you to do Bayesian marginalization without really any significant additional cost on training. It's a bit more sensitive test time and so on. It's also deep kernel learning, which basically just requires a single forward pass through the model and you get sort of some representation of some uncertainty. And these procedures were adopted in practice. And so if I go like to some more domain-specific conference, like some workshop or conference on materials engineering, things like that, I'll see lots and lots of talks using Bayesian optimization, Gaussian processes, neural networks with epistemic uncertainty representation, etc. So this is really useful in practice, but it's very hard to kind of go beyond the useful approximations I think we developed without doing a significantly making sort of a really significant 10-year kind of style moonshot landing kind of investment in those directions, which I think is worth making. Secondly, there's the advent of LLMs, and that did sort of change things in practice. So like we went from million parameter models to billion parameter models, and the role of epistemic uncertainty is also a little bit less clear, I think, in some instances when we're working with LLMs. And so this is just a real technical challenge, and I think we're just sort of barely starting to scratch the surface of how to think about it. But the motivation is absolutely there. I think it's really greater with these big models than it is for virtually any other model class. And in this sense, I don't know how anyone could not be a Bayesian. Like, how can anyone say, I don't want to represent epistemic uncertainty? I don't like using jargon. So there's aleatoric uncertainty, which means irreducible uncertainty. Often associated, like we have given a data set, we have some noise on the data set, there's nothing we can do about it. That's aleatoric uncertainty. Epistemic uncertainty is uncertainty that's reducible with more information. And we believe that uncertainty is there. And there's even an argument that that might be the only uncertainty in the world, right? Like things that seem intrinsically random, like I could roll a dice, and it might seem like, okay, there's a 1/6 probability that it'll land on any one of the sides. But if I had enough information, like if I could sort of exactly know the strength of the throw, the wind in the air, the friction on the table, and I had the right physical model, I should be able to predict exactly what side it's going to land on with each throw. So that's just saying, okay, the more information we gather, the less uncertainty we have, even for this process that somehow seems intrinsically random. And physicists, modern physicists now, probably do believe that some aspects of the universe are intrinsically random, radioactive decay and things like this. But many others have not historically, like Einstein was a determinist. And so he would have believed that the only uncertainty there is epistemic uncertainty. And I think for practical purposes, that's not an unreasonable belief. And so it's absolutely crucial that we try to model it in some way. To not do it is just to do something that's mathematically incorrect and could come at a huge cost. There's also a change I think that's happened in this movement to LLMs in the way that people think about data. So it used to be the case that you kind of have a fixed data set and then you throw everything you can at it to get the best possible performance. Maybe you have some scientific problem and you just really want to do well and you're limited by computation and other things to some extent. But it's not the case that you have this sort of trade-off to manage for a given computational budget between the size of the data and the size of the model. And so that's described by these scaling laws, like chinchilla scaling laws. And that is starting to become the assumption in mainstream machine learning, that you have almost like an arbitrary amount of data and you have a fixed computational budget and you want the best possible performance under that computational budget. In that case, rather than trying to be more Bayesian or something like this, it could actually make sense just to use more data.
But the other huge benefit, though, is because you mentioned, that for whatever reasons that we're still trying to understand, these large neural networks, deep neural networks have this kind of simplicity, bias towards simplicity, right? And marginalization is the ultimate Occam's razor. It's like Occam's guillotine or something that really can force models, force you to select, let's say, the simplest model that's consistent with the data in a sense. So I think there's possibly more to gain there, like just, trying to understand in computationally tractable ways how to pull in more of those effects of marginalization, like on inference. I mean, is that true?
Absolutely, yes. So Bayesian marginalization has this automatic Occam's razor bias. And I actually started working on Bayesian deep learning, ironically, when I saw a talk on optimization, which might be viewed as almost the opposite of being Bayesian. So Ori Nosal gave a talk at Cornell where I was initially a faculty, and he was presenting on small batch biases, basically, of stochastic optimizers. And he had this figure where he was contrasting flat optima with sharp optima, and he had this horizontal translation of the loss landscape. And under that translation, the flat minimum still had reasonably good test loss, but the sharp minimum had very bad test loss. And so he was saying, this is why we want to do stochastic optimization with small batches, because it's going to be more likely to find these flat solutions. And in some sense, like the other optimizers, like his LBFGS and some were too good. They were like converging to these sharp minima. And if like you just care about minimizing loss, then maybe that's not bad behavior, but generalization depends more than on just getting a low value of loss, at least for the loss functions that we're using. And so I saw that figure and I thought, well, this is actually really great motivation to be Bayesian, because if you're being Bayesian, you're not just betting everything on one solution, you're integrating under sort of a flip version of that curve. And so automatically most of the volume will be in these flat regions. And that's so much more elegant than approaching this from the optimization perspective, where you have to say then, okay, I need to rigorously define what it means to be flat. Like maybe it's going to be like the largest eigenvalue of the Hessian, maybe it's going to be flatness
tensor or something like that.
Exactly, yeah. Maybe flatness in random directions versus sharpest directions. Maybe it needs to be parameterization invariance. Like that's been often a criticism of discussions around flatness, etc. That it's most ways of measuring flatness are parameterization invariant. I have thoughts about that separately, but anyway, you might then look at Fisher matrices or something. Okay, so then once you've decided on what it means to be flat, and no one will completely agree with you, or most people will strongly disagree, whatever you choose, then you have to decide like how much am I going to penalize sharpness? No one will really know what to do about that either. And like the idea is you want to build a loss function that is a better proxy for generalization by accounting for things like flatness, but it's just this really messy rabbit hole. Whereas if you're just doing marginalization, this is all happening under the hood. You don't need to worry about it. And so that's really elegant. And then there's Occam's razor in terms of model selection. And I recommend that everyone check out chapter 28 of David Mackay's Information Theory and Inference Learning algorithms book. It's titled Occam's razor. And I don't agree with some of the stuff in that chapter. And in fact, we wrote a paper about this on Bayesian model selection and marginal likelihood. But it's a very beautiful description of automatic Occam's razor. And he has these just extraordinary visualizations to try to demonstrate how that's possible. So he has like these also, everyday examples as well, like this idea that maybe you have like a block behind a tree. But if you had X-ray vision, it would appear to be like 2 blocks of equal height and color, or 10 blocks or something like this. But given that you don't have X-ray vision and you don't think this is a trick question, you'd be pretty confident it's got to be 1 block. And this seems like some manifestation of Occam's razor. And you might try to rationalize this by saying, well, it would be just a remarkable coincidence to have 2 blocks standing next to each other of equal height and color. But he argues that this is actually a quantifiable consequence of doing Bayesian marginalization. And so he basically has this conceptualization where you have all possible data sets on a horizontal axis and the probability of generating a particular data set under your model on the vertical axis. And that's the marginal likelihood, the probability you would generate your training data under your model prior. And so if you have the 1 block model, you're not going to be able to generate very many different data sets. So most of the data sets on the horizontal axis have no support, no PD given them. But the ones that it can generate, it's going to have to give a lot of probability for because this is a proper normalizable probability density. Similarly, if you have a 10 block model, you can generate all sorts of different types of observations, but you're going to have to sort of spread that mass more thinly because this is like a proper normalizable probability density. And so for a particular data set that's consistent with both of these models, like the block behind the tree example, the 1 block model is actually going to have significantly more probability. And this is even not factoring into account the idea that maybe we have some prior preference for simplicity and that there's like, we think that 1 block is more likely than 10 blocks or something like that. He's just forget about this ratio of prior odds and only consider this ratio of marginal likelihoods. And so it's just a beautiful demonstration of how Bayesian inference automatically encapsulates a notion of Occam's razor. And this is just a fundamental question in science. Like if you have arbitrarily many hypotheses that are consistent with any number of observations you can ever record, how do you choose between them? What's the principal way of approaching that problem? And the answer to some extent, I think, is given by Bayesian marginal likelihoods. There are very subtle issues, I think, with some of the ways that this can be done. And so we wrote a paper all about that. But largely speaking, it's something that I think people should acquaint themselves with because it really is sort of getting at something very fundamental and it has extraordinary practical value.
What was that paper?
The one that we were sort of looking at. So we have a paper called Bayesian model selection, the marginal likelihood and generalization. And so that paper is really trying to sell 2 sides of the story. On the one hand, it's trying to convince the readers that the marginal likelihood is something quite extraordinary and that there's a reason we should be interested in it. Because if it isn't, then if you haven't heard of it, like why even read criticisms of it if it's something that doesn't matter? The other part of the paper is questioning whether it's answering exactly the question we want to be asking when we're doing model selection towards trying to achieve the best possible generalization. And so the question that the marginal likelihood answers is what is the probability that my prior generated the training data that's different than what is the probability that my posterior, after I've observed the data, is going to lead to reasonable predictions? And so we can construct examples that really illustrate this difference. Like you could have a uniform prior over solutions that you expect to be easily identifiable from the data. And so the posterior will contract very significantly around something that will actually be quite reasonable and make reasonable predictions, but the marginal likelihood will be really bad. And so we construct all sorts of examples where there's actually a misalignment between the marginal likelihood and generalization for these reasons. You could also overfit, even though you have sort of some robustness to overfitting. Like if you're considering arbitrarily many models, you could just get super unlucky and have a model which is like a point mass prior on something that can only generate that training data set, but isn't going to do anything reasonable. So the marginal likelihood might prefer that, but it's not going to lead you to a model that's going to make good predictions. It is very useful as sort of a heuristic for model selection in many instances. It's got incredible practical value in learning things like hyperparameters that control complexity in Gaussian processes. And I think it often is the right tool for scientific hypothesis testing, which is subtly different. And so this is actually a real historical example. So there was a dispute between statisticians at Columbia University thought that general relativity was not the explanation for Mercury's irregular orbit. It's called Mercury's perihelion. There must be some hidden planet or some orbital debris or something like that. And so Bayesian statisticians actually went ahead and computed the marginal likelihood associated with general relativity explaining Mercury's orbit versus these alternative hypotheses like some modification to Newtonian gravity, etc. And because general relativity was so falsifiable, like its predictions were so sharp and consistent with what we observed, it had orders of magnitude greater marginal likelihood than something like a modification to Newtonian physics where you have to have some distribution over the modification might sort of enable you to explain what we see, but it also is going to generate other data